started. So today we are going to um, talk about image processing, which is a low-level visions that in our schedule. So today we are going to talk about mainly about image filterings. So, but first we are going to talk a little bit about digital cameras, how the image being formed in the digital cameras. And then after that, we are going to discuss about image filterings. And so we started first with linear shift invariant system. So we are going to discuss what it is, and then why it is it important. And then we will discuss about the convolutions operations. And then after that, we'll talk about linear filters, followed by a nonlinear filters. All right. So these are the topics that we are going to cover today. So let's get started with digital cameras. So if we look at the image sensing pipeline, how the camera capture the image, right? So basically capturing the image with digital camera is nothing but working with a light signal or a light wave. So the light wave came into the optics, and then it interact with the air pressure. So yesterday we already learned about the air pressure, which is controlling the size of the hole that allow the light to pass through. So and then we can also limit the amount of light, not only by the aperture but also the shutter speed. All right. So that's about the physical of the cameras. And then after that, when the light wave hit the sensor, so there are basically mainly two sensor, which is CCD and CMOS. That is the sensor that are being used in the cameras. So this sensor are capturing a continuous wavelength from the light that being hit on the sensor. And then there's a sensor chip that process this analog signal. And then it has the ADC, which is analog digital converter, that convert a wavelength into a digital signal. All right. So that's what we get, a raw image. And then that raw image is being further processed by a unit called image signal processing. So then until, like, for example, it performing a denoising, sharpen the image, perform some white balance, and then compress the data. And then finally, you're going to get the image in the type of JPEG, for example, or JPG. So if you have a digital cameras in your camera, you can set either to capture a raw image or to capture a compressed version image, which is basically that's what we normally use. For example, we got a JPEG, which is roughly about 1 to 2 megabyte per image, but the raw image would be like up to 5-10 megabyte. It depends on the resolution that you want to capture. So that is the image sensing pipeline. That's how the digital camera works behind the scene. Okay. So every time you press the button the shutter button, so that's how these are the steps that the camera took to generate your the image. All right. So if you're talking about the digital imaging sensing, so as I mentioned, there are mainly two versions or two types of the sensor, which is CCD, which is stand for charged couple device, and the other one would be a CMOS, which stand for complementary metal oxide semiconductor. So these are the two main types of sensor that are being used in digital cameras. So in CCD, so every sensor, so this is a more semiconductor forming in the form of a grid, right? So in a 2D grid. So each of the sensor here, each of the sensor here will be hit by a light wave. So that's what the photons. So this sensor convert a photon into the electron, So that is keeping a chart of the electron. All right. And then to read out, to convert from the electron, to convert from the charge into a voltage, so that we can convert a voltage into a pixel value. So in CCD, it has a charge to voltage conversions at the ends of the sensor at the bottom here. So to read out every pixel in the sensor, it need to read line by line. All right. So you cannot just randomly read it. You need to read it line by line so that the converter can convert the signal, the chart, into the voltage. So that's the drawback of the CCD. So it's hard to read out the image. So it is also more expensive. So to solve that problems, CMOS come in with built-in individual chart to voltage conversions. If you see a red, the orange triangle within the cell, so that's where the built-in chart to voltage conversions. So what it does is that it allow us to random access to individual pixel. All right. So we don't have to read the sensor line by line, but we can access individual sensor randomly, because it has its own conversions, its own converters. So that's the advantage of CMOS, and also it's very cheap to manufacturers, and also it can expose to like a very long exposure time as well. Right. So these are a basic or the main types of sensor that are being used in digital camera nowadays. So it depends on the manufacturer which types of sensor they are being used. Right. So that's how the image being created using a digital cameras. So let's now talk about the types of the images. So what are the types of images? So there are mainly three types of the image. So first, color image. Second, the grayscale image. And third, binary image. All right. So the color image mainly, oops. So let's first talk about the binary image. All right. So the binary image, so each an individual pixel can contain only 0 or 1. So if it's black, it will be 0. If it's white pixel, it will be 1. So it's just 0 and 1. All right. So that's the binary image representations. For the grayscale image representations, so each pixel can have a value ranging from 0 to 25 to 255. If the image is 0, it will be black, completely black. And then if the pixel value will be 255, it will be completely white. So the range, so the number in between will be ranging from like black to white. All right. So it could have a value ranging from 0 to 255. So that's a grayscale. All right. And then the color image we use nowadays, it consists of 3 channels, which is red, green, and blue. Like in the lab yesterday, when we print out the dimensions or the shape of the image, we can see the width, the height, and the channel, which is 3 channels. So these are the 3 channels that basically the color image can be represented as. All right, red, green, and blue. And then when this 3 value of red channel, green channel, and blue channel summed up, we're gonna get a single value for each and individual pixel in our image. All right. So yeah, just know him if you're in the AI world. So I met him in Bangkok. The image itself, it is, we can say that the image it are being sampled and quantized. What do I mean by the image is sample? So the image is sample, which means that we are converting the analog signal into a discrete signal. All right, because the image is created by a light. So the light wave is analog or continuous signal. So in order to represent the image, we have to sample a continuous wave of light into a discrete wave of light, into a discrete representation, which is in terms of pixel. All right. And then for each pixel, quantization means you are converting the value into a certain range. Into a certain range means that, so if we are capturing the color image, if we are capturing color image, so for each pixel, we have to quantize the value of red, green, and blue. So which is converting the voltage into a value from 0 to 255 for each channel. All right. So when in a grayscale image, the pixel value ranging from 0 to 255, in color image, for each channels, red, green, and blue, they also have a value ranging from 0 to 255 for each channels. So if you, for example, in one pixel, in this pixel, some pixel here, let's say that it has a red value of 100, a blue value of 50, and then a green value of 200. So they will sum this up. So we're going to get the final value. Can you imagine that? So let me show you what I mean by that value. Yeah. Mm-hmm. So if you look at this color, all right. So let's say that we have some pixel that is in this color. Let's say this color. All right. If you look at the RGB value, so that's the red value. That's the value of the red color. This is the value of green color. This is the value of blue color. So if we move this to completely, this is not completely red, right? It should be completely red. So as you can see here, we got 255 for red and the other zeros. If we have completely green, not completely green, somewhere around here, this is completely green. So as you can see, the red channel and blue channel become zeros and green become 255. And then it is completely blue. That's completely blue. All right. If it is a mixing between this number, for example, it probably be the orange color here. So orange color is a combination of red and green for this value, but no blue. All right. So that's how the three channels combine this value into a color. All right. A value into this certain range, which is 255, 0 to 255 for each channels. So sample mean converting a continuous wavelength into a discrete, which is a pixel, which is a pixel in terms of a grid, right? A pixel, which is a 2D, two-dimension grid. So that is a discrete. All right. So if, for example, let me make it clear here. For example, we have a light wave coming in. So this is a continuous value, right? So this is a continuous value for this pixel. Let's say this is the pixel that we are talking about. So we want a sample. So we probably sample a value from here, right? We sample a value from here as the value of this pixel. So it could be like probably 300. And then we quantize this into 3 channels RGB to get this pixel value. All right, so that's how the pixel being sampled and quantized. All right, so when we are talking about the resolutions of the image, all right, so resolution is a sampling parameters. It's defined in DPI dot per inches, so which means that in 1 inches, how many pixels are there? So the high inches, which means that we have a very high resolution image. Right. Let's say that when you're printing something, or when you are saving a Microsoft Word to a PDF, there's a parameters that you can set how many how many PDI you want, which means that how PDF versions of your Microsoft Word being saved, how much the resolutions of that. You can control the number of PDI. Okay. So this is giving you the example of 10 PDI, which means 10 dot or 10 pixel in 1 inch. So as you increase the number of DPI, the edge of the circle getting sharper and sharper. So which means the image has a high resolutions when you increase the DPI. All right. So that's the resolutions. So the image, as I discussed, the image, it is nothing but we are converting a wavelength into a discrete, so that we can view the image as a functions. All right. So if we view the image as a function of f, which is a projections from which is a projections from R square, all right, which is a projection from 2D, all right, into R, into 1D, okay? So if we have a functions of X, Y, so give the intensity at positions X, Y here. So for example, from this image, we have X and Y dimensions over here. And then we can view this image as a functions of f. So the highest of this one is the pixel value. All right. So we can see it as the functions. And the image, it is projected onto what we call a Cartesian coordinates. So yesterday we heard about homogeneous coordinate, but basically in the image, we are using a Cartesian coordinate, right? So the Cartesian coordinates, the origin is started at the top left corners. So 0, 0 start here, not here. Okay, so start at the top left, and then moving X in the green directions, and then moving Y in the green, and then moving X from top to bottoms. All right, so that's the Cartesians of coordinates of the image. When we are talking about the pixel as 0, 0, which means that it is the top left. If you are talking about the image at the bottom right, which means it is equal to the width and the height of the image. Let's say that this image is 200 pixel height and then 300 pixel width. So this last position will be 300 at the location 200 and 200. All right. So this is X, this is Y. So that's the last pixel over there. All right. So that's how we represent the image in Cartesian coordinates. So yesterday we we learn about basic transformations about the image. We learn about geometric transformations of the image, which mean rotation, translation, scaling. So that's called geometric. Okay, it did nothing with the pixel value. It just did something with the pixel locations, not the value itself. All right, so that's why it's called geometric transformations. So, but if you're going to do some image processing, which means that we are transforming the value of the pixel itself. Okay, so as we discussed, the image can be seen as a functions. So we can apply some operations to the image, which means apply some value, some operator to the pixel value. For example, if we have this image as a functions of f of x and y, and then we are saying that we are going to add every pixel, we are going to add the value of every pixel with 20. So which means that we are brightening the image. For every pixel, we are brightening, which means adding the value to the pixel. All right, so that's why the image seems to be brighter. So, and if we are saying that we are going to negative x, so which means we are flipping the image. So you can either do a additions, multiplications, and also divide some value from the pixel value. So that's all the operator that you can do with the image. All right. So that's the image. So now let's turn our attentions to the filters. So that is another operations that we can apply to the image, so that we can transform the image into some other form, maybe enhance the qualities, maybe reduce some noise. So the goal of filters is to form a new image whose pixel values are a combinations of the original pixel value. So why do we need to filter? So like I said, by filtering, we might enhance some information, so then we can get a more useful information from the image. For example, we might be able to extract an edges, a contour to understand the shape of the objects within the image, or we can get the edges to find the boundaries of an area within the image. And also we can use a filter to enhance the image, like removing a noise or sharpens the edges within the image. All right, so that is the goal of the filters operations. So first, let's talk about the most simple filter that we can use, which is a linear filter. So in order to modify the pixel in the image, so what we can do is that we can say that, for example, we have the image with some pixel value, and then we plug it into some system so that we get some result, which is a modified versions of that pixel value. All right, so the image filtering is the operation that modifying the pixel value, okay, based on a local neighbor of each pixel. So before we dive into how each and individual's linear filter works, let us talk about one of the very important concept of image processing, that is a linear shift invariant system, right? So what is the linear shift invariant system? A system can be considered as a linear shift invariance if we have a functions f of x, we plug that in, and then it gives out the function g of x, in which a system have two properties, that is linearity and shift invariance, right? So what do I mean by that? So let's look at the linearity property first. So let's say that you have two functions. You have two functions f1 and f2. And then you plug F1, you feed F1 into linear shift invariant system. You get the output of G of 1. And also you plug in the F2 into the system. You get a G of 2. So if you provide or if you plug in a combinations of F1 and F2, that is alpha F1 plus alpha F2, you also get a combinations of the output of the two as well. So that's a linearity property. Okay. So if you plug in individual, you get individual. But if you plug in a combinations of the two, you get combinations of the two. So that's what we call a linearity property. So what about a shift invariance? What about shift invariance? So for example, you have these functions f of x, this signal, you feed it into a system, and then you got this signal out. But for example, if you shift a signal by amount of a, if you shift it, this is the original, you shift it first, and then you plug that into a system, the output will be the same, but shift by the same amount. So that's what we call shift invariance. So by shifting the signal, the input signal, it doesn't change the output. It doesn't change the shape of output, but just also shifting the output as well. So as you can see, input is the same, output is the same, it's the same form, but the only so that's what we call shift invariance. Shift invariance means you are shipping something, but the output is not changed. You still get the same output. All right. So that's what we call shift invariance. So let's look at the examples of the image or the cameras. For example, you have a lens here, which is have a focus on F. All right, have a focus on F. So if you're moving this plane back to G, which is will be what you will get a defocused image, right? So your image is being focused at these locations. This is your image plane, this line over here. This line over here is your image plane. So, and then the image is being focused here with this length. And then if you move the image plane back to here, so this is where the image get defocused. All right. So how this system related to the linear shift invariant system is that so if you increase the brightness, so if you increase the light that pass through the lens here, so the image that is being projected onto F or onto G will also be brightened as well. So it brighten both of them. It doesn't matter whether it is being F or it is being G. If you pass more light, both of them are going to brighten. And what about the shift invariant? So if the object move in the scene, the object that is being projected onto the image plane at the focus also move, as well as the object at the defocus image will also move. All right, so that's the shift invariance properties. Yeah. No, this is the lens. Yeah. Yeah, that's if the first image plane. No, we can view the entire thing as the linear shift invariance. So this is your camera, right? This is your camera. You can view this camera as the LSIS system. So what we are talking about here, we are saying that these cameras is being a linear ship invariant system. Okay, so why it is being a linear ship invariant? So what we are talking is that first, this is the first image. So this is F, right? We plug in the input and then we got the output as G. So which means that we are moving the image plane back here. So the question is, if we are moving this image plane to G, will the system still hold these two property? So if it is still hold these two property, which means that this camera is a linear ship invariant system. That's what that's what our questions, right? So to prove this, the first thing is that to prove the linearity, so we pass in more light. So if the image at F over here is brightened, so F is brightened, we pass that into the linear system. G has to also brighten as well. Because if F change, G have to change in the same way. All right. So if you defocus the image and then pass into more light, it doesn't matter whether the image at F or G, they are both brightened. Okay. And then for the ship invariance, if the scene move, for example, you have an object over here, and then at F, the object is being somewhere around here. And also the object that is in the defocus also being here. And then if the object move here, so for example, in the focus, the object will be somewhere around here. So in the defocus should be somewhere around here as well. If the object move in F, the object at G should also move in the same directions. So that's what we call ship invariance. Okay. So now let's talk about one of the most important concept in either computer visions or machine learning, which is convolutions. All right. So the convolutions of two functions, f of x and g of x. So we are saying that the convolutions of f of x convolve with h of x, some functions, some system. All right, we're gonna get g of x. So this equal to the integral of f of tau, h x minus tau over tau. So how it is work? So as you can see from here, instead of h of x, we have h of x minus tau. So this is h of tau and then f of x. So what we are going to do is we are going to convolve these two functions to get g of x. All right. So what we are going to do is that first we are flipping this h2 minus tau. So because we want to get these functions. All right. So we flip it first, and then we move it into x. We move to x. So that's what we got, h of x minus tau. And then to perform the integral with a function f at tau, we are mapping these two functions. So they meet at location x. And then you are performing the integral at this location. You're going to get a single value. So that's what we call a convolutions, right? In one dimensional. So we are talking about the signal in one convolutional, in one dimensional first, in one dimension first, right? So if you want to convolve a signal f of x with h of x for every positions, what you have to do is that you just move this h of x to infinity and then slide it through here. slide it to the functions f of x. So you're gonna get a new value like that. So this is a result of f of x convolved with h of x. All right, so that's a convolutions of one-dimensional signal. So for example here, if you have a signal processing that you're performing a convolution between two signal, so the you have this blue one, which is the f of x, and then no h of x, no f of x, and then the red one is h of x. So you convolve these two, you're gonna end up with this triangle, black triangle here. So that's a convolutions of two signal. All right. So the same way as this, the one down below here. So you convolve two signal, you end up with another signal. That's a result of the convolutions of the two signal. That's a 1D. All right. So why convolution is considered as a linear shift invariant system? So let's say that we have this function G1 and G2, which is equal to these two equations of convolutions, right? So this is a equations of convolutions over here. So to prove that these convolutions is can be considered as a linear shift invariant system. So which means that convolutions has to hold two property. That is first, a linearity, and second is linear, it's a shift invariant, right? So it has to hold these two property. So if we, so we know that in order for any operator to be a linearity, if we perform some operations in their combination, for example, we perform the additions here, a linearity, a combination of the two. So this is G1, this is G2, right? So we just extract this alpha and beta out. So you're going to get these two equations. So finally, you end up with G plus 1, G1 plus G2. You're going to get alpha 1 plus alpha 1 G, alpha G1 plus beta G1, which is equal to this value, this one. All right. If you plug in a combinations of input, you're going to get out the combination, the same combinations of the output. So that's mean its whole linearity property. All right. And the next one, we have to prove that it is the shift invariance property is also whole. So how to prove it? So we are letting that this is the convolutions of g of x. So we substitute the because it's shift, right? So we shift the signal by amount of a. So we minus a from this equation. So we're gonna get the integral f of tau minus a multiply h of x minus tau integral over tau. All right. So that we substitute tau minus a as mu. So we're gonna end up with f of mu multiply h of x minus a minus mu integral over mu. So that finally we're gonna get g of x minus a, which means that a convolutions operator hold a shift invariance property, because even we shift the signal, we still get the result, the same result. Okay. So the question is, when we feed in a functions f of x, a signal into h, and then we get out g of x. So how can we find h of x? What is the what is h of x is doing with our signal? So we want to know that. For example, you are giving a black box, all right, and then you can feed in a signal, and then you receive the output, but you want to know what is this black box is doing. So how can we find the the function h over here. So the function h over here, we can say that a function h of x, it is integral of some functions with h of x minus tau over tau. So which means that we have to find what input f will produce that g of t is equal to h. All right, because we want to know h, right? So which means that if we passing in a signal f, we want the output g to be is equal to h, right? Because we want to know h. If we pass it in into a system, if we can get the output g is equal to h, which means that the system is what it does with our signal. So how can we find it? So what we have are something called unit impulse functions. All right. So unit impulse function is a very thin signal and very tall signal. All right. So this delta here is unit impulse functions. So if we plug this in, which is if you integrate any functions with a very thin and very tall functions, you're gonna get the same value. It means you multiply everything with 1, you're gonna get that value. That's what you can say. Yeah, area is close to 0, right? So when you take the integral, you get 1, value of 1. All right. So which means you get the identical of that value out. All right. So what we can do is we plug something in, a unit impulse here. We plug that in. So the thing that is came out, we call the impulse response, which is the same thing, which is h. So that's how we know how the system is working. Okay, where do you lose it? Mm-hmm. Mm-hmm. Yeah. Mm-hmm. 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 Yeah. So we are doing right now. So the picture is two-dimensional image, two-dimensional signal, right? So, but what we are doing now, we are just demonstrating for simplicity with one-dimensional signal. All right. So if we are talking about one-dimensional signal, which means that we have this, and then we have a wave of something. We have a wave of something. This is what we call one-dimensional signal. All right. But the image is two-dimensional, right? It has x and y. All right, and then it have f of x and y as a function of each point over here. That's two dimensions. But what we are doing here, we are doing one dimensions, which is only the value along x axis. So consider a value from a continuous signal, a wavelength, something like that, right? So to make it clear, much clearer, we'll move to 2D. All right, to maybe move 2D. So the linearity property, it has like commutative and associative. So let me come back with this later. So let's consider a 2D. Let's consider a 2D from here. So here it's come 2D. All right. So you have the image, which is a function of f, a function f with the size of m and n. Okay. So if we have this system, or we call it a kernels or a mask or filters. So that's what we call. So if we have a convolutions operations over here, so we have a functions f, and then we want to produce a new output, which is g. right? So what you have to do is you convolve f with h. All right, you convolve f with h. So what you have to do first, if you look at this function h, so at the location I and j, you first flip it. All right, you first flip it. For example, here you have a kernel of 3 by 3. You have a kernel of 3 by 3. So the 0 0 would be start, and then the middle would be in the center here. 0 0 h 0 0. All right, and then h of 1 and 1 will be over here. Let me write it. All right, so let's start with 0 0 over here, right? 0, and then 1 1 over here, 1 2, 1 3, 1 4, and so on and so forth. All right, and then this is what -1 and -1. So since we are having this negative over here, so which means that we have to flip this. We have to flip this around. We have to flip the edge first before we perform a convolutions. All right. Every time you perform convolution, you have the kernel will be flipped first because it has this negative value over here. All right. So this is your image. The white one is your image. Oops. So you flip the kernel vertically and then horizontally, and then you convolve the image at locations n, m with this kernel, and then you can produce the output at locations I, j, which is a summations of multiplications of every pixel under the kernels. So that's what the convolution does, right? So that's how it works. So you have a kernels of this value. So you slide it through the image. All right. Every time it's sliding through, it is perform a multiplication for each and individual pixel, and then sum it up to end up with the final value that you can produce the new image. All right. So that's how the convolution works. No, it cannot be stopped because it's a GIF, it's animations. So how we calculate this one? So let's take this 114. So you have to multiply this. So you are mapping with this, right? To get this 114. A real? Yeah, it will come later in slides. Yeah, that will be later in slides. So yeah, 3 by 3, you multiply this. 0 with 0, -1 with 0, 0 with 0. Yeah, element wise over here. So you multiply element wise, this, and then also this, and this. So you sum everything up now. You sum it all up, it will be equal to 114. Yeah, can you check whether it is 114? So what we're gonna get now, we're gonna get 300, right? 300 from here, which is multiplied with 5. And then we minus that 113 out, and then we minus 73. Yeah, 73. Yeah, it will be 114. Yeah, so that's how it works. Okay. So that's how the convolution works. you're sliding a kernels over the image, so then it's produce the new image. The kernel can be any size. It depends on your choice. Okay, so the size will be affect this output value. All right. So for example, as you can see here, we are using 3x3 kernels. And then, so the zero around the border here, we call a padding. So why we do padding? Because we want to keep the image to have the same dimensions, right? To have the same dimensions. So the image is blue area here, which is 5x5. So if we don't do a padding here, and then we do a convolutions of 3x3, the size of the image will be reduced to probably 3x3, I guess. So we do a padding to keep the new image. All right. So yes, which one? So let's look at this one first, the 114. Yeah, so 114 here. So 114, right? This one. So this one is a resultant of this multiply with this, multiply with this, multiply with this. All right. So, and then this multiply with that, and this element multiply with that, and then this multiply, gonna get zero. This is you're gonna get minus 73. This is you're gonna get zero, right? So which means that this is 300, 300 minus 113 minus 73 here. So you end up with 114. Right, and then you ship it 1 pixel, you're gonna get the second pixel over here. And then you ship it again, 1 pixel, you're gonna end up with minus 22, minus 26 over here. Yeah, you ship one and then move down one pixel. All right. You got the idea how the convolution works, right? So the there's a what we call a border problems. So to add the border, so we can add or not add the border. It is both are okay, but for adding the border, we just want to keep the size of output image to be the same size as the input image. So um, we can we so the how can we padding? So that's what we call padding. So what are the way that we can pad it, the borders? So first we are just padding with zero. All right, we're padding with zero, so it will become black. Or we can pad it each side by warping. What do I mean by warping? So this is a second technique, like in order to pad, right? So warping means that you are padding this size by flipping the thing over here. So which means this side is flipped and then padded. This is the padding area. All right, you flip it, and then this size over here, you flip it and then pad it over there. Same thing. You are flipping this area and then pad it into that one. All right. So and then every corner you also flip another corner around there and then pad it into this area. All right. And another technique that we can pad is called clamp, which means that we just replicate the value of this last pixel, and then we just replicate it. Just copy the value of this border pixel and then put it into the padding area. All right. These are the padding techniques. Yeah. Yeah. Wrap it just you swap this to this. So let's say this is your let's say this is your image, right? This is your image. And then this is the border. All right, this is the border area. So warping means you are taking this side and then put it into this side of the padding area. Yeah. Yeah. So let's say this one. So let's say this. Let me draw it again. So let's say this is your image. Okay. This is your image. And then this is the border. So let's say this one is 2, 5, 10, 20. Okay. So by warping means that you put 2 over here, you put 5 over here, you put 10 over here, you put 20 over here. That's a padding by warping. Same for the other side, you just copy, and then upper and lower. And then for the corner here, you just copy this corner into this corner pixel because there's another pixel over here. And then for this corner, you just copy that to that. So that's a warping. All right.
It looks like the global map, right? When okay, the right side we can see the America, so we want that the left side and the right side can next to each other, and that yeah, convolutional can go through that one to detect something between the left side, the right side. Is the idea, right?
Yeah, yeah, right. And for the cramping, it's nothing but you just, so this is your border, right? This is your border. For the cramping, this is your border, border pixel. All right. For the cramping. And then this is the padding area. This is padding area. So whatever value is here, you just copy it. You just copy it into there. Replicate. That's what we call replicating. All right. Yeah. Just copy it. Just copy it to into a padding area. So that's what cramping. All right. Mirroring. It just also it just copy the area and then flip it. That's it. All right. For example, this part, you see this part over here, it just flip it into that one. That's what mirroring. Let me draw this. So mirror means, for example, you have something here. It is very similar to the cramped, but if you have many, if you're padding more than one, so it will not be similar to cramping. So for example, this is your pixel, right? So this is your image. This is your image. And then this is your padding area, all right? The white one padding area over here. So let's say you have pixel value 10, 5, 7, okay? And then you want to pad 3 pixel. You want to pad 3 pixel. Let's say you want to pad 3 pixel. All right. So mirroring means that you're copying. So let me use another color. So these are your padding pixel, right? This is your padding pixel. Okay. So mirroring means that you are copying this 7 into this last pixel. It's flipping mirror. Mirror means opposite, right? And then you copy the 5 into this, and then you copy the 10 into this. That's mirroring. But if you're which is the 10, and then you copy to here, it will be similar to the cramping. Yeah. Yeah. So, yeah, you just, yeah. So that's the technique how we do a padding, right? So when we do a convolutions, so yeah. So the purpose of padding is to keep the image to retain the same size as the input image. Output to be the same size as the input image. So that's the purpose of adding border. All right, so let's have a visualizations, like you said, the real image. So if we do a convolutions of this image with these kernels, with these filters, all right, so it's 0 everywhere except the one at the middle that is 1. So what do you think it will do? If you convolve every pixel in this image with this kernel, you're slicing this kernel through this every pixels of the image. What is the result? What is the behavior of this filters? Hmm? All right. So what it does is that there's no change,
Nothing.
right?
Nothing.
Yeah, there is no change because when we multiply the neighbor with zeros, it get nothing but just that 0 in the middle, right?
Oh, but in case that is we have the border, right? If we have padding, it will no change. But if if we have no border, we will lose the border of the original image.
Yeah, right. If you have if you don't padding, if you don't
Yeah.
pad the image, the pixel around the border of the image, we will lose that. Yeah. And then what about this one? What about everything zeros except this one? What is this filter will do with the image? If you convolve this filter with the image, what is the result? So you're shifting the image to the right 1 pixel, right? So because this is the middle one. So you shift the image 1 pixel to the right. Filters. Okay. And if you're using these filters, like every kernel's elements is equal to 1. So this is what we call box filters. So it will enhance, all right, it will enhance the pixel, or it will be brighten every pixel in the image. All right. So that's the box filters. And if you normalize, all right, so if you have a box filters and then normalize it, you're gonna get kind of blurry image. Instead of a saturated image, we're gonna get some sort of a blurry because we normalize the value. All right. And as you can see, if we apply this normalized box filters, the image kind of blurry or smooth out, right? Kind of blurry and smooth, but it doesn't seem very natural. If you look at the edge over here, if you look at some sort of this place around there, you can see that it's kind of blocky, right? It's kind of blocky. It's not smooth. It's kind of blocky. So how can we change that? How can we make it look better? So what we can do is that if you see the difference, right? You can see the difference. So what we can do here, we use a fuzzy filters. All right. A fuzzy filter is that the one that is very bright at the centers, and then as it goes out from the center, it's keep darker and darker. All right, so that's what we call a fuzzy one. And then we apply these filters to the image. So it kind of blur the image, but it doesn't have a blocky artifact. All right. So what is that? What is that fuzzy filter? How can we formalize the fuzzy filter using a Gaussian functions? All right. So this is a Gaussian functions. All right. This is the Gaussian kernels. So the Gaussian kernel is nothing but these equations, right? So we are performing at the locations index I and j of the image. So we have this Gaussian kernel. All right, we have the Gaussian kernels over here. So the rule of thumb that how much we can set the size of the Gaussian kernels. So the rule of thumb will be equal to the 2 pi of sigma. All right. So sigma here is the size of the kernel, how the width of the kernel. All right. So as you increase the width of the kernels, you have to increase the size of the kernel, the width of the Gaussians. All right. The sigma over here. All right. If you take a sigma squared, that would be variance. So the sigma is nothing but a distributions within the Gaussian kernel, right? So this is how you define or formulate the fuzzy filter using a Gaussian functions. All right. So what you have to specify is you have to specify the sigma value and the size of the kernel that you want. The size of the kernel means what is the width and the height of this one. So basically k times k. All right. So k should be equal to 2 pi of the sigma. All right. If we have sigma is equal to 3, what is k? What is the size of the kernel should be? Is it 18? 2 times 3.4, right? Times 3. It's 18, right? It's roughly allowed 18. So this one, the size of the kernel will be 18 by 18. Or if you make it 19, it's okay. All right. So that's the kernels, Gaussian kernel. So if you apply the Gaussian smoothing to the image, as you can see, the image getting smoother, but not that blurry, right? It's getting smoother. But if you keep increasing this sigma, which means that the white area is getting bigger and bigger, right? You increase the size of the Gaussian kernels. So the image, the resulted image will be more blurred. All right. So if you keep increasing this sigma, the resulted image will be getting blurry and blurry. So for example, here sigma is equal to 4, sigma is equal to 16. It's getting more blurring, and then yeah. So that's how the Gaussian kernel works. How you can smooth the image. All right. So any questions so far? So if not, so what I'm trying to say here is that instead of by doing a Gaussian smoothing, right? Instead of just performing matrix multiplications like this in 2D, so we can do it in 1D. Right? We can separate it and then do it 1D so that it is more computational optimized, because doing 2D instead of you doing one dimension Gaussian filter instead of 2D Gaussian filter, you're going to save a lot of computational power. All right. So we can separate it. So if you convolve 1D Gaussian filter here and then 1D over there, you're gonna end up with the same thing. So multiply or convolve the input image with one-dimensional Gaussian filter is better. Okay. So if you like do it real quick over here, so there will be if you compare 2D Gaussian filter and then 2 of 1D Gaussian filters, you're gonna see that the multiplications and additions operations will be huge difference. Okay. So that's the linear filters. So that's what we call linear filters, which is a Gaussian kernels, which has a linearity properties and it has a ship invariance properties. Any questions about linear filters? It depends. It depends on what you want. All right. If you want to smooth out, if you want to smooth the image, probably Gaussian kernels is working. You want to smooth it, but the parameters that you have to keep changing to see whether which one is it's okay with you. If you have to keep changing the sigma, because sigma has the effect on the blurring effects of the image, right? The more you increase the sigma, the more image getting blurred. But it depends on how much you want your image to getting blurred. Or sometimes you want to just maybe you want the image to blur out. For example, you want to if you have the image and then it's contain your passport number, you don't want anyone to see your passport number, just apply the box filters to mask it out. All right, because that's going to blur the image. All right. So as you can see here, it's from getting a little bit sharp to kind of blurry image. So that's how they apply the filter to the image. All right. So that's the Gaussian filters. All right. So now let me talk a little bit more about nonlinear filters. All right. So for example, if you have this image with salt and pepper noise, that is the black a little bit black dot over here in the image. All right. And then you apply the Gaussian filters. All right. You apply the Gaussian filter. So as you can see here, the Gaussian filters does not remove that kind of noise. And then also by applying the Gaussian filter in this case, you're losing some informations on the edge of the coin, right? Because it smooth the edge. So that's kind of blurry. So you're losing some informations over there. Okay. So to solve these problems, we can use something called median filters. It's more like the algorithmic filters. So what is the median filter does is that so we have a kernel, right? We have this kernel k by k. Let's say that we have 3 by 3, and then we convolve this kernel. We are going to convolve this kernel with the image. So what we are doing is that we are squaring, all right? We are checking the number under the filters. All right. Let me give you example to be more clear. So this is the image, right? This is the image, and then this is the part of the image that performing filterings. All right. Let's say 3 by 3. You have a kernel of 3 by 3 mapping here. Okay. And then you have a value of pixel that fall under this kernel. For example, you have 5, 6, 8, 10, 20, and 30, 25, 10, and 2. All right. So these are total 9 number. All right. That's a total 9 number. And then what you have to do is that you have to sort. You have to sort the value in this window. and then take the center. So if you sort, let's say that you, oops. Give me a moment. Right. If you sort this number under this kernel, for example, we have 5, 6, 7, 10, blah, 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 until 30, right? Until 30. So let's say that the middle value is 10, right? So we assign this 10 value to the resulted pixel in here. So that's why it's called median filters. So you take the middle value of under the filters, and then you replace that in onto the output filters, output image. Yes, sort and then take the middle value. I'm sorry. Yeah. So here we take example of 3 by 3, right? So there will be a total of 9 numbers. Yeah, there will be a total of 9 number under the kernel here. So you sort that 9 number, you take the middle number. So which means that the number 5, right? The middle number. No, I mean you sort it, right? This is the pixel value. We have 5, 6, 7, 10, 25, blah, 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 until 30. Let's say that last 31. You take the mutant one. So you have 9 value, right? You have 9 value, 4, 4. So you the fifth one in the sorted value, you take that one and then you put it onto the resulted image. No, the kernel matrix, it doesn't have any value. It just define the size of the pixel that we want to see. So it doesn't same as linear. It doesn't have any value, and then it doesn't do any multiplication and additions. It's just doing sorting. Yeah, it just taking the value, the pixel value, and then sort it. No. There is no number here. There's no number. There's nothing. Yeah, it's no, not also nothing. Let me give you an example again. No, this one, it just define the size of the area that you are going to consider. It doesn't have any operation to do. The only operation is that you are sorting the number or the value of the pixel within this region, 3 by 3 region. Okay, so let's say this is your image. This is your image. Maybe like 72 pixel by 72 pixel. And then you are saying that you are going to use a median filter with the size of 3 by 3. Okay, size of 3 by 3. It has no value inside. It just define the boundary. So you map this kernel with the image. So then you look at the image. You look at the image pixel under this kernel. All right, under this kernel, which means that we have nine value here. So let's say that at this location, it is 7. At this locations, it is 10, let's say. And then at these locations, it is 15. At these locations, 20. These locations, 5. And this locations is 25. This locations is 30. And this location is 35. And this location is 40. All right. So what we are doing, what we have to do next, we are going to sort this 9 number from smallest to largest. So we're going to get 5, 7, 10, 15, right? And then 20, 20, 25, 30, 35, and then 40, right? So then you take the middle one, 1, 2, 3, 4, 5, this one, right? 20. And then you mark that as a pixel in the resulted value. So which means that this one will be 20. So you do this for every pixel. Yeah.
We do this for reduce the noise.
Yeah, we do this for reduce this kind of noise, salt and pepper noise.
Yes.
Mm-hmm. Yeah. Not the average, the median. Yeah, the median for all the pixel. It can reduce the noise. So because the Gaussian filters cannot be used to reduce the noise here. It's just blurring the image. So just keep in mind that when we are doing filterings, what we want to do is that we want to enhance the qualities of the image, right? So in this image, it contains a noise we call salt and pepper noise. We want to remove it. But when we apply the Gaussian noise, it doesn't work. The result, we're just getting a blur image, right? So that's why they invented another filters called median to reduce this noise, right? To remove this noise from the image so that we get the resulted image without any noise, all right? But this as I explained, we cannot use a convolutions operations with this kind of filters because it's nonlinear, right? Because you're just sorting things and then pick up something. All right. All right. So as you for the median filters, the problem is that as you increase the size of the filters, the image also getting blurry and blurry as well. Okay. So another way of doing of reducing the noise, something like this. So we can what we can do first. Let's revisit the Gaussian smoothing, right? So a Gaussian kernel will look something like this. If we apply this Gaussian into this image, we're gonna get a blurry image, right? As a result. So what we can do is that because for the Gaussians, we apply the Gaussian kernel to every, we give the weight to every pixel under the kernels, right? We're giving a weighted. So what we can do is that we can solve this problem by just not consider some of the pixel that has a value that is very large comparing to the pixel at the centers of the kernels. For example, we are consider we are doing a convolutions for this pixel, right? So this pixel look kind of black, right? So but this pixel look white, right? It has very bright pixel value. So if we consider every value under this kernel, right? So it is going to produce a very blurry image because that's the nature of the Gaussian. So the strategy that we are not giving or considering the image that has a value pixel that is very different from the one that we are currently operating on. So which means that this black value and this white black value. So the black value here is the one that we are operating on. We are working on it. And then this white value have a very high difference between pixel value so that we don't consider it. So we're giving a black dot here because black means 0, right? So which means that we are not considering that area to be computed or to be convolved with the kernels, so that the result that it will get sharper and also reduce the noise as well. All right, and also, for example, this is the pixel that we are considering, that we are operating on. We are doing the convolutions, and then this is bright. This is black. All right, so which means that we don't want to consider this area in the convolutions operations, right? So that's why in our filters, we are replacing it with the black value. All right, so then when you convolve this filter with this image, you're gonna get a kind of clear, no noise around this one. All right, the concept is that you don't consider a pixel that is very different from the one in the middle. All right. So that's the thing that we are doing here, because we are trying to solve the problems of Gaussian kernel, that is consider every pixel under the kernels, giving a weight to every pixel. So to solve this, using a Gaussian kernels to reduce the salt and pepper noise, we are not considering the pixel that is very different from the pixel in the middle. All right, so as a result, as you can see from here, it's remove the salt and pepper noise around this number. So there's another filters that is behaving something like this. So we call a bilateral filters. Okay, so let's imagine that this is the image. Okay, this is the image. The sharp edge over here is an edge, right? For example, you have the image with an edge. With an edge, this is, for example, this is a table, something like that. So we have an edge over here. So the edge is nothing but the change in intensity of the pixel. So we can see the intensity of each pixel as a functions over here. So the sharp falling edge over here indicating the edge within the image. Okay. So if we apply the Gaussian to this image, so what you're going to end up is you're going to end up with the edge that is very smooth, which means it's blurring, the image. Okay. So this part called spatial Gaussian. But we don't want to lose the informations of this very sharp edge, right? Our purpose is we don't want to lose these informations. If we apply Gaussian only, we will lose some information because it will smooth out the edge. So we introduce another factors that we call a brightness Gaussians. All right, we call a brightness Gaussian. So we keep a Gaussian, we multiply this Gaussian. We multiply this Gaussian with the brightness. What do we mean? What do we mean by brightness? We are giving a much more weight to the pixel that has a similar intensity with the pixel that we are interested in. For example, we are performing a convolutions at the red dot over here. And then we are giving more weight to the pixel that has the same or similar intensity, that is the the orange dot over here, but we give a less weight to the dot that has a very different pixel intensity than the red one, that is the green one here. So this is what we get if we are giving the weight to every pixel under the kernels by considering their pixel value, which is the brightness, right? So that we multiply this brightness Gaussians with the normal Gaussian. So we're gonna end up with this kernel. All right. So then we apply this kernel to the image. So we're gonna end up with this result, which has a very sharp edge. It's retain the sharp edge. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yeah. Yeah. Right. So this brightness Gaussian is nothing but you are giving the weight. So the height of each one is the weight that you are giving to each pixel over here and each pixel over here. So the pixel that has the pixel value close or similar to the red dot, you are giving it high value. You're giving it high weight. So that's why you end up with this sort of shape. All right, and then you multiply this with a Gaussian. So you end up with this one. And then you apply this kernel to the original image. So you end up with this output. So that's what we call bilateral filter. Okay. So I'm skip this one. So if we compare the bilateral filters and Gaussian filters, so this is the originals. If you look at the phase, there's a kind of Gaussian noise, right? There's a kind of salt and pepper noise over the phase. So if we apply the Gaussian filter with sigma is equal to 2, so you can see that it's kind of blurry, right? But if you're doing a bilateral, which means that we have two Gaussian, a spatial Gaussian and brightness Gaussian, and then we specify the sigma S here, which is spatial Gaussian equal to 2, and then sigma of bilateral or the brightness is equal to 10. As you can see, it's retained most of the edge, right? It retained most of the edge as well as removing the noise. So you get a much better output image by using a bilateral when comparing to Gaussian. And if you keep increasing the sigma of the Gaussian, the resulted image from the Gaussian filter, you're getting blurry and blurry, right? For example, here from 2, you increase the sigma of the Gaussian to 4, increase the sigma of Gaussian to 4. The middle one getting blurry, and then this one getting a little bit blurry. All right. And then if you keep increasing, this one, if you keep increasing the sigma and then keep changing the sigma, you get some sort of different result. But until if you keep the sigma of the brightness at infinity, and then set the sigma of spatial, which is a Gaussian, to some value, you're gonna get a Gaussian again. Okay. Yeah. Mm-hmm. No, it difference. From yeah. Yeah. So the portrait over here, what it is doing is that so in your camera it has some lighting source. It has lighting source, right? You have a cameras, and then the portrait mode is working with the depth. It's work. Yeah, it's a portrait. Mm-hmm. 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 It depends on how you take the photos. If you take using a portrait mode, it use a depth of the image. So that's why you see a clear image at the front and then a blurry image at the back. Uh-huh. Oh, yeah. Yeah.
You blur everything out, only this thing more sharper.
Mm-hmm.
Is the background is separate to the front.
Yeah. Yeah. That's the same thing. If you capture which is normal mode, not the depth one. Yeah. Yeah. You blur the background. So that's how it works. That's a bilateral. It depends on the sigma value that you're setting. So yeah. AI can also do that, but basically the image processing is enough to do that. Yeah, the image processing technique is enough to do that, and then it require less amounts of computationals because you don't have to run any models. Yeah, yeah. So that's the bilateral versus Gaussians, right? So that's that's it for the filterings for linear and nonlinear filtering. All right. So we will have a lab. I'll hope that help you implement it. All right. So let's take like um five 5 minutes break, and then we'll come back. So if you have any questions, just feel free to ask. All right. I think let's move to the lab. So maybe hopefully that will help you understand more what we have been discussing about the filtering. All right. So the materials has been uploaded to the platform, so you can download from there both images that we are going to use in the lab and also the Jupyter notebook. You can download from there. Okay. So let's first look at let's first look at thresholding first. All right, thresholding is mean you're doing something with the pixel value. For example, simple thresholding, which means you are limiting or you are setting the value that you want to select. For example, you want to retain the image only if it's greater than the thresholds. Otherwise, you set it to zeros. So, or another approach would be the adaptive thresholding, right? So let's jump into the code. So let's see how it works, and then let's see the result. Okay, let's just run the first cell. So what we are doing here, so let's say that we have the black and white image, which is this one. This is the original image, and then we apply the binary thresholdings. So what do we mean by binary threshold? So in order to threshold the image, we can use the functions called cv.threshold, providing the image and then providing the value of the pixel that you want to threshold. So here we are given 127, right? 127. And then we specify what kind of thresholding that we want. All right. So for example, the binary means that, oh, okay. So binary means that if the value greater than the threshold, we will set it to 1. Otherwise, we will set it to zeros. All right. So this means that this is our original image. And then we are saying that the threshold is 127 because the pixel value is ranging from 0 to 255, right? So we are saying that any pixel in the original image, if the pixel value greater than 127, we will set it to 1, which is white. Otherwise, we will be zeros, which is black over here. All right. So we can get that. Or otherwise, we can do the inverse. So it's just the opposite one. If it greater than 127, we set it to black. Otherwise, we set it to white. Okay. So we by specifying the threshold binary inverse. Okay. And another threshold that we can do is the truncate, right? Truncate T0s and T0 inverts. It is kind of similar, work the similar way. You specify the threshold that you like, and then choose any threshold algorithm that you want. It's just going to cut off. So in this image, it's just showing you what is each threshold operation means. For example, the binary threshold inverted, truncated, right? Truncated. So if we are setting the value to 127, so which means that that's the maximum value. So any pixel value that greater than 127 will get truncated to 127. If it's less than 127, we just keep it as it is. So that's why this is a result, right? So this area of pixel, it has a value greater than 127. So that's why it get truncated to 127. So you can try to change this value. Let's say that we are using let's say 200. 200. All right, so this is a result that we got. All right, this is a result that we got. You get this smaller area. All right, and then this one is getting like kind of truncated around there. Or we lower the value to, let's say, 50. And then this is the result, right? This is the result if we lower the threshold, right? So that's the thresholding, right? So if we do adaptive thresholding, so this is what we call adaptive thresholding. So this is the original image, all right, and then we specify the global thresholding, which is 127. If the pixel value greater than 127, we set it in terms of adaptive. So we are taking the average around the pixel value, right? That's what we call adaptive mean thresholding. We are taking the average around. So this is the functions, right? You call adaptive. You call this adaptive, and then you specify the image, and then you specify the adaptive algorithm that you want to do, right? And then you calculate the average. So this is what you got. All right. So that's thresholding. So let's move to image filterings that we are talking about. It's either Gaussians, it's either linear or nonlinear models. All right. So let's first read in the image. All right. So we are reading in the image here. So this is what we are doing, averaging, or in other words, it's called, what is it? It's the average filter, right? So in this slice, we have the average filter. Where is it? Box, mean, median. Yeah, somewhere around here. We have the average filters. Okay. So what we are doing here, so this is the original image, and then we define this kernel. Okay, we define the size of the kernel to be 3 by 3, and then we define. So let's look at what is the value of the kernel. All right, so here's the value of the kernels, the value inside the kernels. So we specify that for each value is 0.11. So what we are like just randomly specify 1 and divided by the kernel size square. You can specify any value here you like. Okay. So what I'm showing you here is how to define your own filters. All right, you can define your own filters. Maybe you can doing something like a kernels is equal to something like this. Okay, maybe probably something like this. This is your kernels. Okay, and then you apply that kernel. For example, if we are doing that, we apply this kernel. Oops, what happened? Kernel is not NumPy. Oh, you have to specify it in NumPy. So kernels is equal to np.array here. All right, so that's how you can define your own kernels. All right, so what I'm showing you here is just how can we define our own kernel. So you can come up with any kernel you like. So by specifying the NumPy array and then using cv.filter 2d and then apply the kernels. All right, so this is what we got by applying every everything's -1 except the one in the middles. I'm sorry? The -1? It is, I don't remember. Let's see. It's a depth image. Yeah, so we can look at the documentations of the CV, yeah. So if we look at the definitions, yeah. So filter 2D here. So it is going to be the depth of this one. Yeah. So that's how you apply the filters, the filter that you define yourself. Okay. So now let's doing some image smoothing. So we have learned the way that how can we smoothing the image by using the averagings, Gaussians, median, bilateral. Okay, so all these functions has a methods in OpenCV, so that we can call those methods to apply to the to our image. So what we are doing here, we are reading in the image, specify the kernel size, okay, and then we apply these 4 functions to do the image smoothings from blurry. So the blurry will be the averagings, and then apply the Gaussian blur. So we specify the kernel size over here, and then the image, and then this is what we're applying the medians, and then bilateral, right? For the bilaterals, we have to specify the size of the kernels as well as the sigma, right? So in our lecture, we say that for the bilateral, we have 2 sigma to control here, right? We have sigma S and sigma B, okay? We have sigma S and sigma B. So that's what we are specifying here, sigma S and sigma B, right? So let's see that result. So as you can see from here, this is using averaging image smoothings. This is the one that we are using Gaussian, medians, and bilaterals. All right. So maybe you probably wanna try to change this to parameters or even the kernel size, so that you can see the difference between the result of each smoothing filters. All right. For example, in the median, or in the medians, we can see the averaging. We can see that the effects of changing the kernel size that has the effects on the resulted image. For example, using these functions, the kernel size of 3.5 and 7.9, and then applying the blur functions, which is the averaging filter. So as you can see, if the kernel size goes up, the more blur image become. All right, so that's the effects of different kernel size using a median, I mean the averagings. What about the median blur? So the median blur, so it gives like a similar effect. So as the kernel size getting like bigger and bigger, the image getting more blur. Okay. So the thing here is that you are just specifying the image and the size of the kernel. That's it for applying, for smoothing out the image.
Average sub all the pixel.
Sum and divided by the number of elements in the kernels. For example, if you have the 3 by 3, you have to divide that by 9. Yeah, so that's the averaging. So for the Gaussian blur, we know that controlling the value of sigma has some effect on the resulted image, right? For example, in Gaussian, if you remember that in our Gaussian here, if we keep changing this sigma value, so the size of the Gaussian will like change, so that when the size of the Gaussian change, it has the effect on the how smooth or how blur the image is, right? So from this code, we can see that we change the sigma from 0.1 and then increasing to 1 and 2 and 5. You can see that the image getting blurred and blurred, right? So you can play around with this by specifying the size of the Gaussians, right? So remember that the size of the Gaussian, which is the value k over here, should be roughly about 2 times pi times the value of sigma. So that's the size of the k. The ideal size, the rule of thumb, how you set the kernel size. Okay. So which means that whatever the value of sigma here, if we want to make it follow a rule of thumb, so this one should be equal to 2 pi sigma. So if the sigma is equal to 0.1, what is the optimal size of the k? 0.5. What is the optimum size of k?
3.
It should be roughly about 3, right? Roughly about 3. And if sigma is equal to 1, the optimal size of k would be somewhere around 6, right? So that's the optimum size. So you can keep changing this kernel size with respect to the sigma value. Okay, so let's say that if we are setting this one without considering the rule of thumb. So as you can see, it's getting blurred and blurred. This is very much more blurred because we are using a very, very big kernels with a very high sigma value, right? So if we keep reducing this to something like 3 by 3. So yeah, so this, yeah, no difference, I would say. That's not much difference. Okay. So that's how the sigma values and the size of the filters affect the result after we apply the filter to the image. Okay. And for the bilateral, so bilateral here. So for the bilateral, we have at least 3 parameters to control. Okay, so we have a sigma of Gaussians, and then we have a sigma of brightness to control, as well as the size of the kernels, which is k, that we have to control. All right, so let's see that for example, we have the value. This is the size of the kernels. This is a sigma of spatials, or we call sigma color. And then we have a sigma space here, which is the sigma spatial. This is a sigma color is equal to what I call sigma brightness. Okay, color is the brightness. And then if the sigma space means sigma spatial, because spatial is mean space. Okay, so in bilateral, we have to specify these 3 parameters. So let's say that let's see what it affect the value of the result image. Okay. So for example, if the size of the kernels is 9. And then the sigma brightness 75. And then the sigma spatial is also 75. And as we increase the sigma brightness or space, we will get some sort of different result. If, for example, if we keep, let me change this sigma, what is it? Sigma brightness to infinity, a very high value. Let me change this. So if we take this sigma color to a very high value, so that the result should be equal to what we apply a Gaussian, all right? So as we discussed here, if the sigma of the brightness or the sigma color goes to infinity, which is very high, so the bilateral filter will behave like a Gaussian smoothing, all right? So this is what the result is, the last one here. So I increased a sigma color to, let's say 10,000, it's very high. So that's why it behaves like a Gaussian smoothing over here. All right. So let's introduce some noise. So that's what we call a salt and pepper noise. So what we are doing here, we are reading in the image, all right? And then here we are generating the noise by using a random function, just random value, because we wanted to generate a pepper and salt noise. And then here we apply the noise to the image. So the noise will be, what is it? The noise will be salt and pepper, it would be a black and white, right? So if the salt noise, it will be white. And then if the pepper noise, it will be 0. So we are setting the salt and pepper noise inserted into the image. And then we are applying these four kernels to the image that is being introduced, the salt and pepper noise. Okay, so here's the image after we apply a salt and pepper noise, black and white dot, and then we apply the kernels, or we apply the filters, averagings, and then Gaussians. As you can see, Gaussian cannot remove the salt and pepper noise, right? And this median filters can somehow deal with salt and pepper noise. Also, the bilateral filters cannot handle a salt and pepper noise that well, like the Gaussian as well. All right. So what if we want to introduce some Gaussian noise? So the Gaussian noise we can generate using a random a normal functions, right? Because Gaussian is a normal functions. So you have to specify mean and standard deviations to generate a Gaussian. So then we can insert that Gaussian noise into the image. All right. And we apply the other 4 filters over here. So this is what we call Gaussian noise, right? After adding the Gaussian noise into the image and then applying the filters, averagings, Gaussians, medians, and bilaterals. Okay. As you can see, if we added the Gaussian noise, the Gaussian filters can remove that noise, but we lose some information because if you compare the image to the original, it's kind of blurry. All right, but the bilaterals can handle the noise a little bit better because it still retain some kind of sharpness around the edges of the image. All right. All right, you probably maybe we have some time. You can try this implementing this sort of block of code to gets your hand on how to apply the filter to the image. Okay, maybe let's take 10 minutes. You can finish this out, this block of code. So if you have any questions during this, maybe you can ask. Yeah, there's our friends saying that after changing like parameters, filters parameters, that and the nose of this woman still looks kind of creepy. Okay, so I think maybe Photoshop can help, or maybe nowadays we can use Gen AI to regenerate this image. Yeah, probably that's gonna work. Yeah. So while you're doing this, the homework for this week. So there is no submissions, but for you to do it for maybe for your mini projects would be adding these functions, which is applying the filters to the image, added to the app that I give you, the demo app, right? So you remember this app, right? So the demo one here. So you're adding the functions that look similar like this. Okay. Give me a moment. It's trying to connect to. So so in the demo app, we are going to add the functions, the filter function. For example, if we switch to a filter options here, so we can select, for example, converting the image to grayscale, something like that. And then adding a filter blur image, right? So we can select the size of the kernels, so then we can blurring the image. All right, so this is the first one that I want you to add these functions to the demo projects that I give, that the template. Okay, adding this. All right, so this is the functions that you should add to the demo projects. And then in the afternoon, we will do this thing. In the afternoon, we will do canny edge detection, so that you're going to add these functions to perform the edge detection, something like this in the afternoon. Okay. So for this week, you have the homework to perform this, to add the functions into the applications. Yeah. Yeah. Yeah, you have you Mhm. So maybe in the future you don't need to do it like the function that I did. So because I have converting the image to grayscale, applying the filters. Maybe you add different filters, for example, adding bilaterals, adding Gaussians, adding which one you want to implement. Yeah, or you can probably doing some treasuring the image, treasuring the video frames, something like that. So in that exercise, you just may need to read in the image and then fill in this parameters of the function, so that it can produce the results of Gaussian Burr, median filters, and the Laplacians. Yeah. So can you guys implement this? Okay, I think it's not that difficult, right? So you just fill in these parameters.
So, what is the error?
What is that?
Rồi rất là vào.
Okay, so maybe this is another things that may be probably useful. So we didn't cover that, but it's not that difficult to understand. So we call morphological transformations. So there are mainly two types of morphological, which is erosions and dilations. So erosions mean, for example, if you have the image of these letters, and then erosions mean you define kernels, and then you slide a kernels to this image, like what we did in convolutions. And then if the pixel in the original image, it will be considered one, which is white. If all the pixel under the kernels is one. If all right, so let me make that clear. So this technique we can use to sharpen the edges of the objects in the image. For example, if you have a kernels, lying somewhere around here, so this point we'll consider a black, and then if we have a kernels lying somewhere around here, this point will become white because all the points under the kernels is white. So we keep it as it is. But if the point somewhere around here, it has some black dot under the kernels, we keep it as the black one. Right. So let's see the output first. You will understand what it is. So let's do that. So here's the erosions, right? Here's the erosion. It means that we are sliding the kernels. We are sliding the kernels. This is kernel, right? This is kernel. We are sliding this kernel through this image, all right, to the image. Wherever all the elements under this kernel is white, we keep it as white. But if at least one element under that kernels is black, we mark all that black. Okay, so that's why from this very kind of thick J, it's become very thin J. All right, so that's what we call erosions. But dilations working on the opposite side. Okay, dilations working on the opposite side. If we apply dilations, it will increase the size of the white area most likely, because it's just working on the opposite side, saying that if the pixel, if at least one pixel under the kernel is one, we mark that all one. So that's why it increased the size of this white area. All right. So there's also the openings and closing. So the opening is nothing but doing the erosion followed by dilation, which means you shrink it first and then you stretch it out. Okay. So opening means you apply the erosion first and then follow it by dilations. And then closing is the reverse, which is the dilations followed by erosions. Okay, so that's the results from the two. All right, so I think maybe, yeah, this is, if you want to play around with others, you can go around with that, no problem. You guys finished this, right? Mm-hmm. Okay.
I changed the photo size error.
But which one you're saying the kernel size and its error?
So the first one I used the 1000 and 330, right?
Mm-hmm.
Second one, so three, winning one, so it's okay, I can number.
Mm.
I want to change the other side.
Mm-hmm.
Power.
What's the error set?
Side. Okay. Let's see. A side one. Option two. A five.
Yeah.
This is wrong.
So do you specify the kernel size to 4? Basically, we specify the kernel size to the odd number. So it's 3, 5, 7, something like that. Yeah. Maybe you can try it, 7, 9, 11, something like that. So basically, most of the time we specify the kernel size to be even odd number. Yeah. Also for the Gaussian blur, you may try different sigma value. For example, now it's default to 0. Maybe you can try 1, 2, 3, something like that.
We use odd number in kernel size because we need the center pixel, right?
Yeah, right. Otherwise, we won't be able to calculate the centers of the kernels. Yeah.
Let's see.
So if you finish, I think this is it for this morning. So then we'll come back in the afternoon with for feature detections. So we'll start discussing about feature detections in the afternoon. So we will be discussing about edge detections and corner detection in the afternoon. All right. So I'll see you at 1. All right. Good afternoon. So, people online, do you hear us okay?
That's not.
Professor.
Okay, it's good, right?
Yes.
Okay, let's get started for this afternoon class. All right, in the morning, we already learned some basic image processing, which is filterings, linear filters, and non-linear filters, so that we can use those techniques to enhance or to improve the quality of the image. So now, for example, if we already captured the image and then we use a filter to improve the quality of the image, and now let's say that the image has a higher qualities and then it is ready for further process. So next in the computer vision pipeline, after we have the image acquisitions, and now we have performed image processing, which is enhancing some of the quality of the image. Next, we are going to extract some useful informations from the image itself. So that's bring us to the feature detections. So in this class today, we are going to talk about two detection, that is edge detections and corner detections. How can we detect the edge and the corner within the image? So that's what we are going to discuss today, right? So let's first look at the applications of why we need to perform the feature detections. So let's take the applications of automatic panoramas application. For example, you have your iPhone taking a consecutive image, right? And then you want to stitch the image together to create a panorama, like the result here. You're taking many image that has some part of them overlapping to each others. So then you can, from that many separate image, you can construct or you can produce a panoramas out of those images. That's one applications, right? And another application would be a visual SLAM. So what is a SLAM stand for? The simultaneous localizations and mapping, all right? So the SLAM itself, it is used to guiding a robot to navigate around the environment. For example, we have a vacuum cleaners that is navigating around the house. So let's say that it's equipped with the cameras, so that we can use the SLAM techniques to extract, to get the image, perform feature detection to detect, for example, edges, corners within the image, and then we can construct a map so that the robots can navigate through the environment. So that's another applications of feature detections. And another applications, the same thing would be the SLAM. For example, the NASA Mars rovers, they are using a technique SIF features matchings to stitch or to detect the objects within the image. For example, on Mars, the rover taking many image, and then finally NASA want to produce a panorama view of the Mars. So that's the technique they use to stitching the image before sending to Earth. All right, and also they can use the feature detections to detect some obstacle, so that the rovers can navigate navigate through the obstacle in on Mars. And also we can use a feature detections to perform a feature matching for searching for the objects. All right. For example, you do the Google image search, so that you want to search for some objects that is existing within the image. All right. So we can perform a features detections and then do a feature descriptions, so that we can match the image from one image within the another image. All right. So that's another applications. And here's another application that when I was a researcher at National Electronics and Computer Technology Research Center in Thailand. So we are building this automotive part inspections for the company in Thailand. So basically these machines or these equipment basically the company used to buy from Taiwan, which is quite expensive. So then we help them to develop this using computer vision techniques. So the machine itself, what it does is that it is measuring the size of the automotive part that has been produced. For example, the diameters for both sides of the part. So they want to measure the diameters and the height of the objects. All right, so we use the computer visions to detect that and then inspect whether it meets the requirements or not. So the specification is that the errors should not be more than 100 micron. All right, so we have to do some, like for example, subpixel in order to make it very precise. So this is one of the applications of using computer visions and feature detections to in industry. So we can inspect this and then reject whether it is good part or bad part or not. So this is one of the applications. All right. So here's how it works. All right. So here's how it works. So we have a top view camera, side view, and then the bottom view. And then we have this part coming in on the rotor, and then it passed through 3 cameras from different angle, so that's how far it is when we can process the image. So we can identify whether it's good or bad, and then what is the diameters, and then we have a pump, the air pump to pump it out to a correct category, whether it is good or it is a bad part. All right, so that's the application that I and my team we developed for the company in Thailand using computer visions technique. All right, so come next is why do we need to extract features? All right, so for example, in panorama applications, so we want to stitch together, we have 2 images, and then the question is, how do we combine them, right? How do we combine which part of the 2 images need to be merged? All right, so how do we combine them for that? So we can do this by first extracting some features from the 2 images, and then we match those features from one image to another image, which means that we extract the features from the 2 and then finding their correspondent, which means finding the similarity, finding the similar features in another image. So then we can merge them together using some sort of matrix that we will learn later. So that's why we need to extract the features. Okay. So after we extract the features, match the features so that we can calculate for the matrix. So that's what we call homography. So we will learn homography later. So we use that matrix to align the image together so that we can stitch the image together to the right place by using the extracted image features. All right, if you're looking at a features matching pipeline, so we can split it into 3 stages. So the first stage would be a feature detection. That is, we want to identify the interest point within the image. And then we perform a feature descriptions. So what is the feature description? It is how we can extract a feature vectors descriptor surrounding each interest point, which means that what is the characteristic of that point that can be described by a vector. All right. For each features that we detected, we will describe it as a vector, as a signature of that particular feature point. So then we use that descriptor or signature from one image to match it with another signature in another image. So if they are the same point, for example, if this point and this point are the same point, they should have a similar vector. They should have the same signature. All right, so that we know that, all right, this point and this point is the same point. This point and this point is the same point. And we do this for all the point that has a similar, that has a pair in another image, so that we got a pair of the same point between the two, so that we can come up with homography to transform, to match the image together, to stitch them together. So these are the 3 steps in features matching pipeline that we are going to do. All right, so let's start with the first stage in this pipeline, which is feature detections to identify or to find the interest points. All right, let's start with the first algorithms to detect an edge. All right, so we perform the edge detections. So before we detect the edge, let's define what is an edge. So an edge, it is nothing but a rapid change in image intensity within a small regions. For example, if you look at these images, so the one on the left, you can see that the edge within the image has a very rapid change in intensity from this point, from here around this is edge, right? You can see the change in intensity from black to somewhat white, from black to somewhat white. So this sudden change within the small regions of the image, that's what we call an edge. That's how we define the edge. As well as this one, it's changing from black to white, changing from black to white. So that's we call a rapid change in image intensity that can be defined as an edge. All right. So what cause an edge to happen? All right. So there are different types of an edge. For example, we have a surface normal continuity. For example, if you have these objects, and then when we take the image of this, the surface that has a different depth from the image, they have a normal. So normal is nothing but a vector that is perpendicular to the surface. Okay. So what do I mean by normal? Normal is, for example, for this surface on top, the normal is always pointing out from the surface. So the normal of this surface would be pointing out this way, and the normal of this surface would be pointing out this way, and normal of this would be pointing out this way, and normal of this would be pointing out this way, because this is the perpendicular vector. This is a perpendicular vector. This is a perpendicular vector to the surface itself. So if there is a change in surface normals, that also cause edge to happen. Okay. And also the depth discontinuity, which means that this surface and this surface, they appear to be different depth, which means different distance from the cameras. So that's also a cause of continuity. And another one would be the surface color. For example, the white area here and the black area here. So that's the color discontinuity. And the fourth one would be illumination discontinuity, which is this is the shadows of this box, right? So this is the illusions of illuminations of this box. So that's create the edge as well. All right. And also, if we look at the image as a function f of x, f of xy, so an edge can be defined as a steep clip between this changing in intensity of the pixel, right? So if you plot this image intensity as a function, you will get this kind of image, so that the steep over here and the steep somewhere here, that are the edge. These are the edge, right? Because it has steep fault or a steep clip over here. This also steep clip. So these are the edge which for example, there's a changing in intensity, right? So this is one clip, so which correspond to this place. And also this is another edge that is changing intensity, which probably correspond to these clips, right? So that's how we look at the edge, and then that's what causing the edge to happen, right? So for the edge detector, what we want the edge detector to produce is the positions of the edge, the magnitude, that is the strength of the edge, and then the orientations or the directions of the edge. That's what we want from the edge operator to produce for us. And for the performance, we need a high detection rate, good localizations, and low noise sensitivity. So whenever we develop the edge operator, we need to keep this in mind. All right, to make it have a high performance detector. So before we dive into a 2D edge detection, let's first look at the 1D edge detection first. All right. So we'll discuss about the edge detection using gradients. Okay. So the edge is just a rapid change in image intensity. So if we look at this signal or a function f of x in one dimensions, 1D, so we can define that the edge would be this on this falling and rising edge of the signal. All right. So we can, that is the rapid change, right, happen over there. All right. So we by using a basic calculus, we can derive that we can derive the continuous function that represent the amount of change, because we want to find the rapid change, where rapid change happen. That's what we want to find. So we can use a derivative to calculate amount of change in the functions. All right. So if we apply using the first derivative, all right, using the first derivative, there is a partial derivative of f of x. All right, that's what we call the first derivative. We apply the partial derivative to the signal. So what we get is the second, this one, right? We get what we call a local extrema, where we got a sudden change amount, the rapid change, and the amount of the change that is peak at that point. So, and we can take the absolute of that first derivative. So what we get from here is we get a locations that is a peak of the height, and then we get a strength that is the height of the peak itself. So we get both locations and strength of the peak. That is, we can convey that that is an edge happened over at that area, because if we apply the derivative for these functions, we get this peak. So that means there's a sudden change in that area. All right, so we can assume that area has an edge. All right, that's the first way to do, is to use a first derivative. And then if you look at a 2D edge, all right, 2D edge, for example, we have an image here. So the 2D edge, in this image, we have two edges. We have two edges, right? That is a sudden change in the intensity. So we can use a partial derivative of 2D, find a sudden change in the image. All right. So what we can do is that this is what we call a gradient partial derivative, what we call del. That is represent the directions of the change of the rapid change in intensity. For example, we have an image, and then we apply a partial derivative, what we call gradient here, to the image. We will get two components, that is a sudden change in x directions and a sudden change in y directions. All right. So if we apply the partial derivative to the edge that is in the x directions, we're gonna get a components of this x, and then the component of y will be 0. And then if we apply a gradients or partial derivative to the image that has only the edge along the y directions, we're gonna get the x component will be 0, and the y component we will get the component in y directions. And the edge that is not in x or y, but it's in like some angle, so we're gonna get a component of both x and y because there's a sudden change in both directions, x and y. All right. So as I mentioned, to find the edge, we need a magnitude, right? We need a magnitude, we need the locations, and we need the orientations. So to find a magnitude of an edge that is being detected by using a gradients, we can take the absolute of the gradients of the image, which is a square root of, which is a sum of square root, a sum of square, and then take a square root of that. So we get a gradient magnitude. And then to find the orientations of an edge, we can find this delta by using the inverse of the tan, the y component divided by x component. So that's how we find the directions or orientations of an edge. All right. So if we look at the image as a discrete equations, as a discrete operator, so we what we can detect is that to find the x and y components, that is x y component over here. So in discrete, we can find the x and y components of an edge by using these equations. So what is this equation said is that to find the difference between the components or the edge within the image, we need at least 2 neighboring pixels so that we can find the difference between them. So this one, so let's say that we want to find the x component of this value of this point over here. So we need to find the difference between these two, xi plus 1, j plus 1 minus this component, and then this component minus this component, so that we're gonna get the component in x directions, and we do the same for the y direction in this area. All right. So we can implement this gradient operator using a convolution that we learned in the mornings by using these convolutions, kernels. So if you want to find in x directions, it would be a kernel of -1, 1, -1, 1, 1. So we have -1 in x directions, and then if you want to find in y directions, you have -1 in y directions over here. So that's how we perform a convolution to find the edge using a gradient operator. All right. There are many gradient operator that has been developed. For example, one of the most famous kernels to detect the edges would be a Sobel 3x3 over here. So these are the matrix or the convolution kernels that we can apply to the image to detect the x and y components. All right. So we can construct different size of the kernels. So the kernel with the small size, it will have a good localization, which means it gives us a good locations of the edge, but it is very sensitive to noise because it's very small, right? But if we increase the size of the kernels, it will give us a very poor localizations, but it very less sensitive to noise, right? Because the kernel is very large. So it didn't give us exact locations. So here is the result of applying Sobel filters, which is one of the gradient operator. So for example, we have this image and then we apply a Sobel filter. It's either in X directions or Y directions, right? So if you apply the Sobel filter that extract or detect the edges along the X direction, you will get this. And then if you apply a Sobel that detect the edge along the Y direction, you will get this. All right, you can see the difference, right? You can see the difference when we apply the Sobel filter to different direction. For example, here, it's more brighter than this image. So which means that this area, these edges is tend to be in the X direction rather than in the Y direction. So that's why we cannot detect it much in this area. All right. So, and also if we can also calculate the gradient magnitudes from that. So the gradient magnitude is nothing but the sum of square, and then take the square root. All right. So we sum of these two, square this, sum them up, and then take square root. You're gonna get this gradient magnitude. All right. And so after you get this components X and Y and gradient magnitude, how do we judge whether that particular pixel is an edge or not? All right. So the first and the most simple thing we can do is using a threshold, right? If we are saying that a magnitude of that particular pixel is less than some threshold, it's not an edge. But if it's equal to or greater than, we consider it as an edge. All right, so that's one single threshold. And we can do better than that. We probably going with hysteresis base, which means that we have two thresholds. So if the magnitude of the gradients less than T0, that point will not be considered as an edge. But if it is greater than or equal to T1, we consider it as an edge. And if it is between 0 and 1, it depends on whether its neighbor being an edge or not. If its neighbor being an edge, we can consider it as an edge. So we'll see that later how it works. All right, but this is one way to go to classify whether which pixel is an edge or not. All right. So this is how this is a result of example of how we can extract the edges. So we have X component, Y component. So sum them up, take a square, sum them up, take a square root, we get the magnitude. And then from this magnitude, we take a threshold so that we get an edge from this one, a clear edge, or at which pixel is an edge. We can identify that for now. All right. So now we know that we can use a Gaussian to find a sudden change in the image by detecting a peak, right? So we can do further. We can do further to detect an edge. So what we did is that we take a first derivative of that and then take a peak to be classified as an edge. But if we take a second derivative of this, so we can find a sudden change again. We can find a sudden change. It's just different methods, okay? It's just different methods. The one that we talked before is we are using gradients, but the one that we are talking now is Laplacian, okay? Laplacian is a second derivative of these functions. We take a derivative of Gaussian. So Laplacian is we can get a Laplacian by taking the derivative of the Gaussian. So we are taking the derivative again. So we will find what we call a zero crossing. So now instead of finding a peak, we just find a zero crossing so that it's indicate an edge. Okay, so you are taking a derivative of these functions. You're gonna get this function. You're gonna get this function. So wherever we have zero crossings, that's indicate an edge. Okay. So Laplacians can be denoted as del square. Okay. So we can take that and then find the zero crossings. So we can either find the x components and y component as well. All right. So the things to note here is that when we are taking a Laplacian as an edge detector, Laplacian does not provide us directions. It provides only the locations and the magnitude, right? It does not tell you the directions of an edge. So I'll skip this one. It's just a similar thing. So yeah. So we can apply this convolution mask to be able to apply a Laplacian operator to detect an edge. All right. So as you can see, as you might notice here, by using this convolution mask, we can find the x and y component. But if we apply this mask, it likely to fail when we have an edge in these directions, right? Because this is zero, this is also zero. So it cannot find the edge that is, let's say 45 degree in each directions here. So how can we solve this one? So we solve by adding one over here, and then increasing this value so that it be able to detect the edge that is 45 degrees both. All right, so here's the result of how when we apply a Laplacian operator to the image. So we can get the x and y locations, and then we can calculate the magnitude at each at each pixel, and then find a zero crossings at that location. So then we can identify that as an edge. All right, so that's the result of Laplacian operator using to detect the edge. So of course, when we are working with the image, it's not totally a noise-free image, right? Even though we already apply some filters, so it doesn't mean that we completely remove all the noise. There probably there's some noise, right? For example, here's an edge, right? And then if you look at this image, we can view this function, right? Function as this signal. So we get this signal that is a sudden change over here, indicating the edge. This is the edge, right? So when we apply the gradients operator to these functions, we probably end up with something like this. All right, so we wouldn't be able to find an edge in this case. So how can we handle this? How can we handle such a noise effect that is being conducted in the image? So what we can do is that we can apply a Gaussian first, a Gaussian kernel or Gaussian filter. We can apply this to smooth out the noise, right? So if we apply this Gaussian, through this function to this function, entire functions. So this is a result of applying Gaussian. So we can smooth out noise. We can smooth out this noise, and then we apply a gradients. We can apply a gradients to detect the peak, which is a sudden change. All right. So whenever you have a noise images, so you apply a smoothing function first for example, Gaussian here to remove the noise, and then performing edge detections by using a gradient operator. So that's how we handle a noise. Or in that case, we can save one operator. We don't need to do gradient first and then applying Gaussian first and then applying gradients. So we can do it all together, which means that we applying this gradient first, and then we apply the results of this into the image later. So by using this one, the gradients of Gaussian, so we call the derivative of Gaussian, which is these functions, right? So this graph in the middle is the result of applying this one with this one. Okay, so you are applying the gradients to the Gaussian. You're applying the gradient to the Gaussian, so that you're gonna end up with this image, because the Gaussian is where you find the zero crossing, right? If you apply the Gaussians, you're gonna get a zero crossing. So that's how you get a zero crossing. So after that, you apply this derivative of Gaussian to the signal. You're gonna get this value. You're gonna get this graph below. Yeah, yeah. Mm-hmm. Yeah, yeah, yeah. So we don't have to do many steps, right? So if you look at this image, you have to perform first Gaussians, and then after that you perform the Gaussians, and then you take a derivative, the gradients again. All right. So instead of doing that, we are combining the two. We are combining the two operations to one, and then applying to the image later. So that's what we call a derivative of Gaussian. All right. And then we can also do the same thing with a Laplacian of the Gaussian. So we multiplying the Laplacians to the Gaussian. So that's what we call the Laplacians of Gaussian. All right. So this is what we get, Laplacians. So we can use to find a zero crossing as well. All right. So if we compare a Gaussians and a Laplacians, so this is the kernels. This is the kernels. So we can look at the kernels, which is a Gaussian kernel or a Laplacian kernel. So on the left side here is the derivative of the Gaussians. So we can apply these kernels to extract the edge along with x directions. So we can apply this kernel to detect an edge along x, and then apply this kernel to extract the edge along y directions. All right. And then for the Laplacian of the Gaussian, you can apply these functions. You can apply this kernel, so that you're going to get both the x and y directions, but just only the magnitude, not the directions of the edge. All right, so these are different types of Gaussian and Laplacian. So if you compare the Gaussian and Laplacian kernels, so the Gaussian would be provide both locations, magnitude, and the directions. Okay, but the Laplacians of Gaussian only provide you with the locations of an edge. All right, and also the Gaussian used to detect using a maximum, and it is nonlinear operations. It's required two convolutions. On the other hand, for the Laplacians, it uses a zero crossing for detecting an edge, and it is also linear operations, so that you require only one convolutions. All right. So these two operator, it has its own pro and cons, right? So the question is, can we come up with the edge detector that exploit the best characteristic of both and work for for both of them? Yeah. So how can we do that? Can we do that? Yeah. So that's bring us to the canny edge detections. So the canny edge detections algorithm have a 5 steps. So first, in order to perform a canny edge detections, first we perform a noise reductions that's required. And then next we perform a gradient calculations. And then the next step will be non-maximum suppressions. The fourth will be double threshold. And then the last step will be edge tracking by hysteresis. Right. So let's explore one by one. So let's say that you have this image as an input image. Okay. So you first perform a noise reduction by smoothing the image with a Gaussian filters. Okay. You smooth this image with a Gaussian. So that's perform a noise reductions. And then you calculate a gradient. All right. You calculate a gradient. So you compute a gradient using probably a Sobel filters. All right. So when you applying a Sobel operator to the image, you're gonna get this component X and Y components, right? And then you use X and Y components to compute the magnitude, which is a sum of square, and then take the square root, a square root of sum of square of those X and Y component. So then you get this gradient magnitude. So by applying the gradients operator, you also get the orientations at each pixel, right? So the image below here represent the directions of the image of the pixel, all right? Directions of an edge or the orientation at each pixel, all right? So now if we zoom in, so in gradient magnitude, if we zoom in, you can see that we get a very thick edges. We get a very thick edges here. So how can we make a more precise, a more sharp edge? So that brings us to the step that's what we call a non-maximum suppressions. Okay. So what is a non-maximum suppressions? So here, let's say that we are considering the area of 3 by 3. All right. At each area, we know the gradient magnitude, and we also know the gradient directions. All right. For example, let's take example this area, this area. So let's bring it back. Let's bring it here. So what we are doing here, we are considering whether this red area, this red pixel here, we are considering whether this red pixel should be an edge or not. All right. So what we are doing here is that we are along the gradient directions. So at this pixel, it has a gradient directions in this directions. All right. So what we have to look at is that the pixel along this line. So if we look at a neighbor pixel, which is this black and white, all right. If the pixel, the magnitude, which is the color of this, if the magnitude of the pixel being processed, that is this point, is greater than its neighbor, both of its neighbor, is greater than both of its neighbor, we keep it as an edge. So in this example, we will suppress this one, which means that this pixel will not be considered as an edge because it has a neighbor that has a higher magnitude, which is this white pixel over here. White is 255. Yeah, 255. Black is 0. So this one probably somewhere around 100 something. So it didn't greater than this white pixel. Yeah, but so it's greater than 1, but not this one. So yeah, so it will not be considered as an edge. So in another example also, we are looking at this pixel, and then the gradients of this pixel is these directions. So we are considering this pixel white and then quite dark here. So we look at these two pixels, and we see that this the pixel that we are being processed is not greater than the value, or the magnitude of it is not greater than its neighbor. So then we suppress it. All right, we will not consider that as an edge. All right, but if we look at this area, let's say we are looking at this area, we are looking at this area, all right, and then we consider this pixel, we consider this pixel, and then this pixel has gradient directions along these directions. All right, so we have to look for its neighbor along this line. So we can see that this pixel, it has the value greater than this dark pixel and then this white pixel. So then we can consider this as part of an edge. So we keep it as it is. Okay, so that's how the non-maximum suppressions. So we suppress the one that is not the maximum point. I'm sorry? Mm-hmm. Yeah, yeah. We consider it as a part of an edge, not partially, but it's part of an edge, because what we want here is that we want to, since we have a really thick edge, right? We want to reduce the thickness of the edge. Okay, so after performing the non-maximum suppressions, so as you can see, we have a very, very thin edge after non-maximum suppression. Comparing to this, so now we have a very thin edges. So that's all good now. All right. So then we're not done yet. We still have to perform a threshold, right? To be better, to be for each and every pixel to be considered as an edge, it has to meet this criteria of double threshold. So if a magnitude at any pixel is less than threshold 0, it's not an edge. If it is greater than or equal to, we consider that a strong edge. But if it is between T0 and T1, we consider as a weak edge. All right. So now keep in mind the word weak edge, strong edge, and not an edge. Yeah. So we define T0 and T1 ourselves. T0 is the value of the pixel that you are going to consider whether it's an edge or not. Yeah, T should be 0 from 0 to 255, and T0 need to be less than T1. Yeah. Mm-hmm. So we're not done yet, right? So we have strong edge and weak edge. So we can eliminate the point that are not considered as an edge. We can remove that one. But now we are going to consider the weak edge, whether it should be a part of an edge or not. So that's bring us to what we call edge tracking by hysteresis. Okay, so how can we do that? For example, this is our T1 and T2. Okay, this is our T1. This is T2. And then if we have an edge, that has a gradient magnitude less than, no, this is T0. If you have an edge that has a gradient magnitude less than T0 in this area, it's considered as not an edge. But if we have a pixel that has a gradient magnitude greater than T1, it would be definitely an edge. But the pixel with the gradient magnitude between T0 and T1, this is what we call weak edge. So for this pixel to be considered as part of an edge, we need to consider its neighbor. All right, we need to consider its neighbor. So for example, if this pixel at this location, it is a weak edge, right? Because its magnitude is between T1 and T0. So, but its neighbor, it has become a strong edge somewhere right here. So if any pixel that connect to us, the pixel that being considered as a strong edge, so that weak edge can be considered as an edge. All right, you no. All right, so let's so weak edge, you understand weak edge, right? Okay. So then let's say that this is the edge that in the image, right? So we are so what we are doing now, we are considering whether this pixel in this part should be part of the edge or not. All right. So this part is definitely an edge. This part is definitely an edge. Okay. So now we are going to consider this pixel in this line, whether it should be connected or it should be considered as an edge or not. So first, we are looking at this point. We are looking at this point, pick this pixel, and then we look at its neighbor. We look at its neighbor, which is probably this point, right? Its neighbor probably this point. This point. So we look at its neighbor, this side and this side. So if this blue pixel is connected to the pixel that is a strong edge, so this blue edge will become part of this edge. All right. All right. So we keep doing that for all the pixel. This C. So if we're looking at this point C, right? So this point is not connect to any strong edge, so this one will not be considered as an edge, right? So that's how we do the edge tracking by hysteresis. So as you can see here, we can reduce lots of pixels that can be considered as an edge from here. So it become much clearer. Okay. So here is the example of canny edge detections. So this is the effect of how can we smoothing the parameters, the sigma here. All right. So when you smooth the image with different magnitude of sigma, you're gonna get a different number of edges. Okay. So any questions about edge detections? All right. So if no questions, I will move on to the next. Yeah. Yeah. Your questions? Yeah. Which one? Derivative. No, the derivative, it is basically, it is a calculus, right? So in calculus, so when you're taking a derivative, which means you are calculating, so let me see this one. No, basically the derivative originally, we are, so let's say that we have this sort of functions that is very something like this. So the question is, how can you calculate the area under the curve? Because it is very fuzzy, right? It is very something like that. So you cannot use the triangulations equation to calculate the area, right? So if you are taking the integral or the derivative, you can calculate the area under some curve over here. All right. So what it does is that it is finding the change in directions, finding change in direction. For example, if you're taking the derivative at this point, so what you find is the directions of change. For example, at this point, you will get some vector around there. The tangents, so we call the tangents. Yeah. So it will give you the orientations of that. So that's how that's why we take a derivative. There's it's not that it's not related. So it's related in terms of, so when you want to detect an edge, right? When you want to detect an edge. So the first thing, you smooth it, and the next thing you calculate the gradients. So the calculate the gradient means that you are trying to find the change in intensity of the pixel, right? So what you see here, the white dot and black dot, the white dot is tend to be an edge. We are not saying it is an edge. What is, but at that pixel, there's a sudden change at that pixel, sudden change of intensity, right? So now we are considering individual pixel, not as a whole image. All right. So we are trying to find whether at that pixel, is there any sudden change or not, right? So that's a gradient helping us to find the sudden change at any particular locations. And then we also find whether the change in which directions. So that's what we got from gradient orientations. So we at each pixel in the image, we can find the change in which direction. So this color, if you zoom in closely, it will be just a vector indicating the direction of change. For example, at this location, at this pixel, probably the vector of change would be somewhere, something like that. So it's a vector telling you that which directions that change occur. That's what we call gradients. So that's we got from some sort of derivative. Mm-hmm. Mm. Mm.
And then you can take the derivative of this function,
Mm.
know the direction, and you know the rate of change.
Mm-hmm.
If the rate of change is zero, means that is the flat line, right?
Mm-hmm.
If you have the mountain, something change there.
Mm-hmm.
So the x it change, if they change it, is the x and very technique, no change figure by the what we call it historical.
Mm-hmm.
Make it big of this x, so big like possible.
So yeah, so after we got this one, after we got this magnitude and then orientations, so that's where the derivative help us, all right? So after that, so at this step, we are only consider individual pixel. all right, individual pixel. So in the next step here, so we are still considering each individual pixel separately. Okay, so we want to minimize the number of pixels that can be considered as an edge. So that's why we are trying to remove the thick edge over here, thick pixel. So at this point, we still consider each pixel separately. Now, at this point, the edge, weak edge, strong edge, we are trying to connect the pixel together. All right. So after you got every pixel value, you're trying to connect them together to construct an edge. All right. So any individual pixel to consider as an edge, it has to be strong edge or weak edge that connects to an edge. All right. So a pixel that is being considered as an edge should be a pixel that has classified as a strong edge, which has a pixel value greater than T1. Yeah. So that's how it is related. Okay. Mm-hmm. All right. So next, let's move to corner detections. So what is the corners, right? The corner is where the two edges meet. That's it. All right. So that's a corner means. So we have flat regions, we have an edge, and then if two edges meet, we can consider that as the corners. All right. So there's a rapid change again, but two edges has to be met. So that's what we call the corner. Again, if we apply a gradient to different types of regions of the image, you can see here, if we apply a gradient from flat regions, we don't see any change, both in X and Y directions. But if you apply to the edge regions, you can see the sudden change in both X and Y directions. And also in the corner regions, you can see that one of the edges is correspond to X component, which is this one, and then the other one correspond to the Y component, which means that this edge has a sudden change in X directions, and then this edge has a sudden change in Y directions. Okay. So that's how we can find the applying the image gradient. So if we take the image gradient and then plot it out to see the distributions, all right, plot the values of image gradient, which means that we are taking this image, individual pixel in this image, which is the components of the gradients, right? And then if you plot it onto a space we call a gradient space here, we can see that the distributions of image gradients of the flat regions mostly lying in the middle. And then if an edge, it would be considered as some sort of ellipse, all right? And then a corners, it also have some sort of shape of distribution, different shape. So if we look closely, we can see that if a flat regions, the lambda, which is the diameters of the distribution in X and Y directions, if it is a flat regions, the lambda 1 and lambda 2 are mostly equal in this distribution space. And if it is an edges, it will be an ellipse, which means that the lambda 1 is much larger than lambda 2. All right. And if it is a corners, lambda 1 and lambda 2 are equally equal, but it is very large. All right. So by using this, we can consider, we can detect a corner by using these methods, by using these distributions of determining the lambda 1 and lambda 2. Okay. So if it flat regions, both lambda 1 and lambda 2 are mostly equal, but they are small. If that region is an edge, contain an edge, lambda 1 will be much larger than lambda 2. But if any particular regions contain a corners, lambda 1 and lambda 2 are mostly equal, but they are very large. All right. So that's where we can use Harris technique for Harris corner detections. So we can consider a lambda 1 and lambda 2. So if a lambda has a very small number, so we can consider that flat regions. If lambda 1 or lambda 2, either one, much greater than the others, we can consider that area contain an edge. And then if lambda 1 and lambda 2 both are large and then they are mostly equal, so we can consider that areas contain a corners. All right. So then we can convert this into a functions of R. So we can calculate R by using these equations. So then we can plot that. So if R greater than some threshold, so we can set this threshold. So if we plug in lambda 1 and lambda 2 and K into that, if the value of R happen to be in this area, we consider that as a corners. And if it's fall under this area, we consider that as not a corner in there. So for example, so here's the image, right? Here's the image. And then we apply a gradients. We calculate a corner response, a gradients from this image, right? We calculate that. So we're gonna get this very bright somewhere around the corners. All right. So then after that, we perform some thresholdings and then perform some non-maximum separations because we want the number of pixels to be considered as a corner to be very small. So that's why we do a non-maximum separation. So then we'll get a small number of that. So this non-maximum separation work similar to what we discussed before. Right, and then so that we can perform a threshold, and then we can detect an edge. I mean, a corners. All right. So that's how Harris corner detection works. So you first calculate the gradients, and then plotting the distribution of the gradients at any particular regions, and then calculate lambda 1 and lambda 2. All right, and then using that lambda 1 and lambda 2 to calculate an R. All right, and then having some threshold to see whether the R is greater than or less than the threshold, so that we can detect the corners. So it will become more clear when you're doing the lab. All right, so that's Harris corner detections. So maybe I can explain a little bit more about non-maximum separations over here. So it work a little bit different, but concept is the same, but it's work a little bit different. For example, we have this area, right? So we want to consider whether any pixel, all right, any pixel in here can be considered as part of the corner or not. All right. So we have a windows of site K, let's say 3 by 3. All right. In this 3 by 3, probably this 3 by 3, maybe 5, let's say 5. 1, 2, 3, 4, 5. Let's say 5. We have 5 by 5 over here. All right. So we look around. So this is the middle pixel that we are considering. So within this window, we look around all this within this region to see whether this pixel has a maximum value than others in the windows or not. So as we can see, this pixel itself is black pixel, right? So it's not greater than this pixel. So then we consider that this should not be a part of the corners. And then we slide that over. We slide this over. So if you look at this window, this pixel, the yellow pixel, is not maximum because there is a pixel that has a higher value. So then we suppress this, which means we mark it as 0. But if we slide it into this one as a middle point, so it has a maximum value when comparing to others in the windows. So we keep this pixel. So it's the same concept. Yeah, it's just considering only the center of the sliding. So the center, but before that, we consider only in the directions of the gradients. But this one, we consider everything. We consider everything. We consider every neighbors. Yeah. 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 Right. 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 So that's how Harris corner detection works. So here's another example of that result. So this is the original image, and then we perform smoothings and then calculating the distribution. So this is what we got, plotting out the corner response, and then thresholding the corners response, and then this is what we got finally to detect the edge. I mean the corners. All right. So any questions? So if no questions, let's take 10 minutes break and then come back. We will do a lab. All right. Let's come back. So we are going to start the lab. So maybe hopefully it will help you understand more about the theories and the practical implementation. So you can download this code from the platform. So it would be in the lab 3. So we have Canny, H, and Harris corner detections, and there's a couple of images that we are going to use in this lab. Okay. In this lab, we are going to perform the Canny edge detections. So the step here is that, like I mentioned, first we perform a noise reductions and then perform a gradients calculations in X and Y directions. Perform maximum suppressions and then doing double treasuring and edge trackings, right? So let's first import the library. So now we are going to use this image first. So this is going to be this image. Which one? So lab 3. So we are going to use this image, right? So it's this building. So we are going to use that. So first read in the image, and then we are converting this image into a grayscale, right? And then we have this functions Canny, right? We have these functions Canny. So we have 4 or 5 parameters. That is the image itself, and then here we specify T0 and T1. Okay, we specify T0 and T1, and then here we specify the gradients or the function that we are going to use to calculate the gradients. Okay, so within these functions is going to perform all these 4 or 5 steps for us, right? Let's look at this. So what we are having here, so this is the original image, all right? So and then we use a Canny edge detection methods in OpenCV, and this is the result that we got. I think it's pretty good detecting edges along that image. So I think most of the edges are detected. Or you can change the image to see whether if it only works with the structural image or not. So we can try to do a waterfall. So it is also be able to detect an edge. So if we adjust, so if we try to adjust the threshold here, T1 and T2, so we'll the number of edges that we are detecting probably will be changed. For example, if we change this to 200 and then change this to 100. So 100. So as you can see, the number of edges that are being detected is a little bit smaller, less than the one that we use 50 and 150. So these are the parameters that we have to tune when we are using this sort of algorithm. So the T1 and T0, like we see in our lecture, T1 and T2 play an important roles in detecting an edge using Canny edge detection algorithms. Okay. So so that let's instead of just using complete or using a provided function by OpenCV, let us maybe construct our own edge Canny edge detection so that we can understand how it works really. Okay. So here, what we are doing here is that we are creating a class of canny edge detections, right? So when the class is being initialized, so we perform the image color, converting the color to the grayscale, and then we can set the threshold T0 and T1, and also we are setting the Gaussian blur, Gaussian magnitude. That's what we have to calculate, right? And then also edges. So the first step is that we have to perform the Gaussian blur, which means that we have to smooth out the image. So in this step, we can use a Gaussian blur functions, right? And then specify the kernels and the sigma that we want to blur or to enhance the image to reduce the noise by using a Gaussian kernels, right? So that's the first step. So then second step, we are going to calculate the gradients. So here we are using a Sobel kernels, right? We are using a Sobel kernels to calculate the X and Y components of the gradients. So what we are doing here is that we call a Sobel functions and inputting a Gaussian the resulted image after applying a Gaussian filters, and then we specify the kernel size parameters, and we also specify whether in which direction we want. So here we specify X and Y. So we want X, so that's why this one is 1. All right. So likewise for the Y directions. So we do that. So we're gonna get GX and GY X directions and gradient along Y directions, right? So to calculate the magnitude of the gradients at any pixel locations, so we can use square root of X square plus Y square, right? So that's which is being equal to this formula. Where is it? So which is equal to this formula, how we calculate the gradient magnitude. All right. So for in these functions, what we are doing, what we are getting from this function is the X components, Y components, and the magnitude. All right. So and next we are going to use that to detect an edge. Okay. So what we are doing here first. So here it's just a definitions of the class that we are declaring. Okay. And then we read in the image, and then we initialize the class instance over here. And then we specify T0 and T1, which is equal to 100 and 250. And then step 1, calling the Gaussian blur, doing the filtering, and then calculate the gradients. And then we want to plot to see the intermediate step. All right. And then after that, we can use to detect the edge for the canny edge detections. So let's just run this. All right. So as you can see, the original image and the Gaussian blur, since the image quite not that very noisy, right? So it is very sharp image. So that's why we didn't see much difference after applying after applying the filter, the Gaussian filter. And then after that, we compute this magnitude of the gradients. So this is the magnitude of the gradient. And then this is the final result that we got after the edge detections. All right, so that's how we perform the edge detection using Canny by utilizing the OpenCV. All right, so that's how you implement it. Basically, just this one line of code is enough. Okay, just this one line of code is enough. If you look at what we can play around with this function is T0, T1s, and then this gradients functions. So let's have a look at what are the gradient function that we can use. All right, CV Canny. Where's the functions? It's the function definitions. Okay. So here's the function definitions. Okay. So what we can play around is the threshold 1, threshold 2, which is T0 and T1, and then the gradients. What are the gradients that we want to use? Whether we want to use L2 gradients or we just want to use a regular gradients, L1 and L2. Okay. So here's the formula for L1 and L2. So probably we can try L1. We can try L1 gradients. Let's try it. So this setting this to 0, which means that we are using L1 gradients. If we set this to 1, so which means that we want to use L2 gradients. All right. So let's see. The result a little bit different, I think. Not that significant. Let's see this one. So this is L1. Let me copy this. Let's see the L2. Right? This is L2. This is L1. Okay. So this is L1 and then this is L2. So in this case, I think it doesn't look much difference. It doesn't look much difference. Let's see another image. Properly, it's see the difference between the two. So the thing is you need to fine tune this, what works best, whether L1 or L2, or whether it is, what is the value of T0 and T1 here. Okay, so this is L2 and this is L1. I think probably L2 is working a little bit better. In this case, it depends on the image, whether L1 or L2 is working better, right? Yeah. Yeah, it depends on your objective, and it depends on the original image itself, because we as a human we can justify whether which part should be an edge, which part shouldn't be, right? So we can justify for that as well, and also from our objective whether we want small number of edges or we want a larger number of edges to be present in the image. Right, so that we have to fine tune these 3 parameters: the thresholds and how we calculate the gradients. All right, so that's the Canny edge detections. Mm-hmm. All right, for the Harris, so for the Harris, we have to first compute the gradients, and then what else do we have to do in Harris? So first we have to perform, of course, smoothing if necessary, and then calculating the gradients of the image. All right, and then finding these functions right? So that's what we have to do. So in OpenCV, we have, it's also available because it's a basic functions, right? So let's just run this first. Right, so as you can see, it's quite small here. The red dot there is the corner that this algorithm is detected. All right, so I think it's do a pretty good detections. All right, because even small area, it can detect the corners, but some of them are also missing. Yeah. So here, what we are doing is the same thing, right? Convert the color, and then specifying the. Let me see. I don't remember this. So let's see these functions. What are the parameters? Here is corner. So it has a block size, and it also have to specify the kernel size. Okay. So what we did was this is a block size. This is a kernel size 3 by 3. And the last parameter would be what is it? What is double K? Let me see. The K is Harriet detector free parameters. So the K is this one. All right. So K is here. K is this one. This empirical parameters here. So it should be between 0.04 and 0.06. That's what the optimal value should be. All right. So that's why we are setting it to this 0.04. So maybe we can keep changing this and then changing the size of the kernels. Probably it would be better. Let's set it to 5 by 5 kernels, and then set this to 0.5. Okay. And then this one just performing a maximum suppressions here. So we do this. I think it is no difference, right? Not much difference from here. By increasing, so let's use a very large, really large filter, like 15. So if we use a very large filters, we lost some of the corners. We lost some of the corners that used to be detected. Okay. So that's how it works. Right. So if you look at a Harris response here, let me zoom out. Oops. So here's a Harris response. What is a Harris response? If we look at back into the lecture, Harris response, it is this one where after we compute the gradients and then we compute these functions, that's what we call Harris response. We compute this function and then we gonna get this corner response. So that's the same thing. This is the response where the very bright, I'm not sure you can see that, but I think in your screen you can see that a very bright dot indicating the corners in the image. Okay, so that's the Harris response. Probably I can change the.
Your result cannot see the bright point.
I'm sorry.
Your result difficult to see the bright point.
So let me change.
The Harris response. That means where is the bright? That means maybe it's a corner, right?
Yeah. So
Yes, but your your screen I cannot see the brighter.
okay, let me change the color. Maybe we can see. See map. what else we can select from here? Let me see what can we choose to make it clearer. CMap color. CMap, let me see. Maybe we can use jet. Maybe let's try jets. Okay, so I'm not sure it's better. So you can see this bright dot, red dot over here. This bright red dot, this bright red dot, this is bright red dot. Right, so this is a bright red dot over here. So that's indicating the corners. So these are the bright red dot. Can you see in the screen? Yeah, this is a bright red dot over there. All right. Let me try another, maybe better one. Probably hot. Let me try hot. I'm not sure it's better, not better, because it's white. Is this hot? Yeah, I think jet is better. Yeah, so that's the Harris response, the red corner over there. All right. I'm sorry?
The red one is.
Yeah, the red one indicating the corners here. The red dot right there. The red dot right there. Right there. Right here. These are the red dot. Right. So similarly, let's walk step by step that we can create our own. So we construct similar functions, right, as the canny edge detections. So we first converting the image color to grayscale, compute the Harris response, and then we can plot the Harris response. Let me see if it works. All right, so this is what we are using to detect a marker, okay? A marker corners on the chessboard. So we are doing nothing but just doing a self-contained corner detector using a Harris response over here. So this is the Harris response of the image. So this is the input image, the chessboard. Okay, the chessboard over here. This is the input image. So we are trying to detect a corners of each point in this image, and this is the Harris response. Let me try to change this into jets, so it probably better. So yeah, no, yeah, I'm not sure it's better that this jet. No. What is a good one? So maybe we can do turbo. We can do turbo. Okay. Yeah. So here's the Harris response. So we can see that the corner are being detected somewhere right there. All right. It's very It's a little bit brighter than the other area over here. All right, so that's the Harris response. And this is the result of that. Okay, so if you would play around with this one, so probably you can try to change. So I provided you with two image of the chessboard. So one with that one, and then the other would be kind of similar to this one in a perspective angle. Try to see whether the algorithm can detect all the corner in this image or not, instead of just a flatting 90 degrees. But what if it is in the perspective? How can we tune the algorithm to detect all the corner in this image? So without tuning anything, let's just try. Perspective. No. What's wrong with? Did I spell it wrong? Chessboard. Perspective. PNG. Okay, it's PNG. Okay, so as you can see, it's detected, but I think it's not that good, because if you look closely at this area, it has dot, right? It's not good. It should have only this dot over here at the corner. So maybe can you find out how to tune this output? So because there's a lot of dot, the algorithm is thinking that every point in here is a corner, so it shouldn't be, right? The corner should be only at this point, not this many dots. All right. Probably maybe you can try to tune these parameters. For example, trying to tune the block size and kernel size and the value of the K to see whether what should works for this particular image. That this is the result that is not good, right? So how can we make it very good? So then it look something more like this, to give a sharp corners. So it should be something like .jpg. So yeah, it should be something like this. Only red dot at the corner, not red dot everywhere on the line, right? So maybe I give you some time to try to tune that, to see whether what are the parameters that affect the performance of the algorithm itself.
Dr. Joshak, we can, we can check the result by eyes, right? Is there any techniques that we can check whether the detection is working well or not?
So we have to have a ground truth, right? So
Yes.
in order to check if we want to check any algorithm that it is working correctly or not, and then what is the optimal parameters for that particular algorithm. So we have to have a ground truth for checking that. So for example, when we are calibrating the cameras, so we have a checkboard like the one that I show you. So we know exactly how many corners are there. All right, we know exactly how many corners are there. So we use that as a ground truth. So if the algorithms, or if the parameters that we are setting is correct, so it should it should be able to detect all the corners. All right.
Okay.
Yeah, so
Okay.
it should return all the corner with the positions of the corner correctly, because we can calculate that.
So we use the number of corner as the ground truth to check whether the algorithm is working well or not.
We use the number and the locations
The
of the
location.
pixel. Yeah, the location of the pixel. So for example, let me share the screen.
I'm asking that because there are many cases like if we see the ball directly from the front, or we can see the other views. Sometimes that we need to, as you said, that we can change the parameters to to detect that well. So in case that if we have the route tools and have any solution for that, we can have the lookup parameters and we can compare with the route tool in case that it correctly, that we can know what is the optimal parameters to choose for this case.
Yeah, right. So for example, if we have a ground truth that is indicating that the corner is at these locations, right? So we have a pixel locations. We know the pixel location for sure. Whether in this image at, for example, let's say at location X30 and then Y100, something like that. So if the algorithm with the parameters that we are setting is saying that the corners is at location 30 and 70, so we know that how much it is off from the ground truth. So then we can adjust the parameters. So the way that we adjust the parameters, it shouldn't be manually adjusting. We can do a grid search because, for example, we have 4 parameters here. We have K. Let me see. We have K. We have the K value here. So we know that the K value is between 0.04 to 0.06. So then we can vary that value automatically, and then we can also vary the size of the kernels. So then a combination of this we call a grid search. So we try all the combination of this and then see that what set of parameter that give us a minimum errors, so that we can choose that one.
Yeah, right. Thank you.
I think what possibilities. Okay, I can call now the chess ball we have, let's say 100 corner. We use OpenCV Harris or Kelly Harris. With this parameter, we only have we can only detect 70. So we have a lot of 30, right? So if we know that 30 left, we need to look at it with the route through until we reach like a certain limit, like 95, and we can stop.
Yeah.
And that means a lot of function compare, and then we change the parameter back with this thermal side, the what else, the Gaussian, then we can check.
Yeah.
We know first the corner.
Yeah, right. Yeah.
Line and search, right? Get the parameter, the route through model Y. We're gonna look to
Yeah, right, like that. So the what you call the loss functions, not only the numbers, but it can be the distance between the detected point, detected corners with the ground truth corner. So we can calculate the distance in pixel. Yeah. So yeah, it can. So it has to minimize that error as well. So any questions?
The route truth ways come from human.
Yeah, it's come from us as a human.
Okay.
Yeah, we label it.
we label by myself.
Yeah.
Yeah, sometimes that I think that we don't need to label many much. So if we conservative enough, so we can detect all of the coordinates as a route truth. but sometimes it's not less conservative. We can like compare just the number of corner, I guess, or we can choose one of the corner and hope that we check that our result can meet with the route through that we choose or not.
Mhm.
Yes, this is okay.
Yeah, yeah.
Mm.
So so let me show you the applications of using the corner detections. So let's say that, so in this course, we are going to learn about the camera calibrations as well. So that's where we can use a chessboard to perform a camera calibrations. So let me show you how we do that. So later in the class, we are going to do that. All right. So what is this application is doing is that it is going to capture the corners of the chessboard 20 view, and then it will use those point from the corners to calculate the calibrations or the intrinsic camera parameters. We will learn about all these things in later in the course. For example, if I'm showing this, you can see that it detect one. So we have to, if you move it, it can always like detect it. Okay. So we capture from different angle so that we can calibrate our cameras. So we can know what is the camera intrinsic parameters. All right. So we'll see later what is camera parameters. So we can turn that, something like that. We can turn that into a different perspective. All right. So yeah. So
But why can it not doesn't capture the corner in the of the top?
what's that?
I don't see that it can capture the corner of the top one, right?
Oh, on the top one, I think it just capture the corners, inner corners, not
Oh.
outer. Yeah, it's capture inner corners. Yeah. Mm-hmm. So if let me run that again. So if you can see there, so this corner is not detected, right? So it is detected only inside this area, right? So that, yeah, something like that. So we need, so before we are doing augmented reality, we have to calibrate our cameras. So we are going to do that later in maybe weeks lecture number 5 to do that. All right. Something like that. So what we get here, we're gonna get a camera intrinsic parameters. So we will learn that later in the course.
It's pretty nice, but what is the difference between the color detected in the image? Like I see that it can be blue or red.
It's just a visualizations.
Okay.
Yeah, there's nothing like doing fancy about the color. Yeah.
Yes.
Mhm. So now you have probably 2 homeworks so that you can build up your mini projects. So in the morning we learn about image processing like these filters, and then in the afternoon we learn about edge detections and corner detections. So what I want you to do is to add that into the demo app that I give you, so that it can be another functions of your mini app. For example, here we already did what is it? Filter, right? We already did filters. So like I show you, we can do different kernel blur, and we also can do edge detections. All right, so maybe you can add these functions, probably trying to add cannies, or trying to add corner detections, Harris corner detection into the applications. Okay, or you can add more options rather than just grayscale blur. So probably you can add more filters rather than just Gaussian smoothings. So probably you can add more filter that we learned today into the app.
Okay. Scale. But what fix grayscale?
Yeah, you
Easy, but
yeah, maybe you can add like filters, different filters, and also canny edge detections.
we watch it.
Mhm. So any questions?
Dr. Joshua, in case that someone like who want to enhance their model, like you said, the last one you shared is about the detect the edge, right? So like I saw that there are many applications like sketching that kind of similar things of edge detection, and in case that if someone who want to like fine tuning to their model to enhance that, I think the canny detection cannot be differentiated for back preparation, right?
With what?
I mean the differentiate like gradient descents to to improve the weight, the parameters of the model. Yeah. So if that we cannot use canny, right? Canny just for detection from the original image, and we cannot change the weight inside that.
Yeah, you cannot change the weight inside that, but you can change it real time. So like this, for example. So you can have a parameters that you can trigger it real time. So what do I mean by real time is that, for example here. So if we do filter, right? So but it's manually, not automatically. So let's say we are doing blurring. So as you can see above here, we have a track bar that we can control the size of the kernel, right? So that's how we can control it real time. We can change the parameters for doing this blurry, right? So we have to somehow changing the parameters within these functions, right? For example, if we are using Gaussian something, we have to change the parameters here. But by changing the parameters here, we can have a track bar that we can set those features, and then have a software, the program that we are writing to extract this value, and then apply this value into the result in real time. Okay, but not automatically, but we have to adjust this manually. But the program is able to apply this in real time. For example, I reduced the kernel size. Yeah. So in my demonstration here, the canny, we can apply the threshold, right? See, you can apply the threshold. We can change the threshold. Yeah, something like that. So something like that.
Okay, we can consider to take that parameter as the variables to enhance the approach.
Yeah, right. So we can play around with this one, this threshold.
And plus the vision then.
Yeah. See, it can detect the edge of the letters. Very good, very sharp. Yeah, we can see AIT Vietnam since 1993. Yeah, it's very sharp. Yeah.
Yes, that's pretty nice.
All right. So any questions? So we still have some time left. So let me just briefly introduce this SIFT feature descriptions. So, and then next time we will dive into detail of what is SIFT. Okay. So, we have already discussed about how we can detect a features, right? So either it's edges or corner. So now we can extract a features. Like I mentioned in feature matching pipeline, after we detect a features, we need to find a signature. We need to find a descriptions of each features that we already detected so that we can use it to map between features into images. So that's what we call a feature descriptions. Feature description means we are finding the characteristic or we are finding a signatures of each features that has been detected. So the thing that we are going to learn about feature description will be mostly about SIFT detector. So what is SIFT? So like I mentioned, we have to find the vectors that describe the features in each image so that we can further use it for matchings. So the SIFT detector can be used in application like, for example, you have the image of a bin that contains many objects. So the question is, how can we recognize what are the types of the objects within the image, or even how can we detect the plate license of the car, for example. So, and also, what if we want to write a software to perform the object detections? So if we have an object of interest, for example, this book, and then we want to find this book within a cluster of the book in the scene. So how can we perform the object detections in this scene? All right. So the thing is that we have to find and match the interesting point, or that's what we call features. For example, if we calculate or if we detect the features in this object that we are interested in, so we calculate and features, And then we also calculate features over here, every features in here, whatever we find. And then we are trying to find a matching, a pair of matching, a pair of features that are appear on both images so that we can locate where is the objects of our interest is. All right. So to do this, we are going to use what we call a SIF detector. So SIF stand for Scale Invariance Features Transform. Okay, so it's used for image alignments and 2D objects recognitions. So that's how we do the object detections of or object recognitions, and also we can align the image together. So in this lecture, we are going to discuss about what is an interest point and how can we detect what we call blobs. And then next, how can we use a SIF as a detector? And then after we detect a feature point or interest point using SIF detector, how can we implement or how can we describe each point as a vector or as a features so that we can use for matching between the features from one image to another image. All right, so that's what we are going to discuss. All right, so and what about what is an interest point? All right, so an interest point could be come in different size, different orientations, and brightness, right? So the interest point should be in difference of all this. So what is a good interest point is the point that we can basically remove the variations easily. For example, if we look at this ZD cover, right? So we can see that there could be many potential interest point. So if we look at this, I'm not sure is it tongue or something or not. So it could be a potential interest point, right? That is, if we rotate or increase the brightness of the image, or we taking the image under different conditions of light, but this one still not change. It doesn't change that much. Okay, so so by using this, the interest point can be the point that can be removed some of variations such as orientations and the colors. All right. So by looking at this point, we can see that if we rotate this image back between the two, we can use a rotation matrix to match between the two. All right. So that is the interest point can be. All right. So for example, we can we can like scale up the point in other image, and then we can rotate it so that we can match the image together. So this can be a potential interest point. So to summarize, the potential interest point would be the point that remove variations from the source. So in this example is that the point that we are interested in, which is this red one, it can be matched with other point in other image by just applying scale and orientations. All right, so that we can easily match them together after we applying scale and orientations to that particular point. So, and for this one, it is not interesting, right? Because whatever we are doing here, we cannot see any useful information that we can use to match between different viewpoint. All right. So for the point to be an interesting point, or we call features, it has to have a rich image content. For example, the brightness, the color within the local windows. All right, so it has to have a well-defined representation. So that's what we call a signature. All right, that's what we call signature, so that it can be matching or comparing with other points. All right, it has to have a very good position within the image. All right, and a very good feature, it should be invariance to image orientations and scale, rotation and scaling. Right, invariance mean no matter how you rotate the image, no matter how much you scale the image, that features, the signature of that feature doesn't change. All right, so that's what invariance means. And also, a good feature should be insensitive to light. All right, whenever you change the lighting conditions, it still be able to represent a good signature within that image. So these are the property of what we can consider as a good features point. All right. So if you are saying that if you are consider whether a lines or an edges can be considered as interesting or not, right? So if you look at this image and then we zoom in to this edges or line, we can see that we cannot localize the edge, which means that we cannot find the positions of the edge. So what about the blobs? So the blobs mean the blobs. So the blobs means here a certain patch of an image, right? A small patch within the image. So that's what we call a blob, right? So a blob have a fixed positions. For example, if we look at this image and then we are trying to extract some patches over here. So we can see that this patches over here on the left side, and then we can also find the patches, the similar patches over here on the right side. So instead of just looking at the edge or the line, we are looking at the blob, which is a bigger pictures. I mean, a bigger areas instead of just looking at the line. So a blob is a patch within the image. So if we look at certain area, so we can see that it has a fixed positions and then it has some certain size. So then we can use this kind of property to create a signatures of features within the point, within the image. Right. So let me see. So let me just another slide, just one last slide. Otherwise, it won't be. I won't be too. It will not continue. So yeah. So a blob can be considered as the interest point because the blob has the following property that we already described, that a good feature should have the following property. So a blob can be located easily, and then a blob is also have a certain size. We can also determine its orientations, and also the most important thing, we can formulate or we can describe the signatures of that particular blob, so that a blob can be considered as an interest point because it has all this property. It is be able to locate. It has, we can determine its size, we can determine its orientations, and then we can calculate the signature of that particular blob, so that blob can be considered as interest point or features. Yeah. So next time next class, we will see how can we find the blob using a SIF detector. Okay. But the thing that we are learning today, we are going to use also next time, which is like, for example, Gaussian filters. You're going to see this very often, right? This graph very often, like the signal are Gaussians, and then the results of the Gaussian. So you see that often. Also the derivative of the Gaussians, second derivative of the Gaussian, something like that. So yeah, that's how it the blob can be detected using those techniques as well. So we will talk more detail next week. Yeah. So yeah. Any questions? Yeah. So the homework would be adding the functions that we are learning in these 2 days into a demo app. So it should work like the demo that I show. So we can, for example, add a filter, choosing different filters, and then adjusting the parameters of the filters. Or we can add the functionality like cannies or corners detections to show the corner and the edge in real time. And also we have to be able to adjust the parameters of those algorithm in real time as well. All right, so that's the things to do. All right, so there is no submissions for homework, but this thing you have to build up from week by week, lecture by lecture, so that at the end of lecture, what is it? We have a mini projects presentation, right? So you have to show us what you come up with, all right, on June 20th. So you have to, so after learning from class 1 to class 5 to class 6, so what can you do with those knowledge? How can you come up with some creative from demo app, and then like what else you can add it into? Yeah, probably like you said, you want to add dinosaur into the AR. Yeah, so yeah, like that. So yeah, that's one more options. Or maybe you come up with some combinations of features and then just trying to show that features. So that's, we are going to build up week by week. Okay. All right. Any questions? All right. If no questions, I think maybe this is it for today. I'll see you guys next week. All right. Thank you.
Thank you, Professor.
Yeah.
Thank you, Professor.
Bye bye.
Thank you, Yi. Have a good night.
Oh, have a good day too. Bye bye. Will you back to Thailand today?
Yeah, I'll be back tonight. Yeah, 10 p.m. Yeah, my flight just got rescheduled.
Okay, have a safe flight.
Yeah, thank you. Okay, I'll send you the code. I forgot. I'll send you the code for the labs that you
Yeah.
are going to lead. Yeah.
Yeah. Okay. See ya.
Okay, see ya.
Okay, bye bye. Good night all.